Hi, glad you're here. Sit back, breathe, get comfy, dim the lights, maybe grab some popcorn, and let's drift all the way back to the very first moment of everything. Once, there was nothing. No space, no time, no light. Then, about 13.8 billion years ago, the Big Bang happened, the sudden expansion of space itself. Energy stretched into reality. Particles formed, atoms followed, and light finally escaped the cosmic fog. Galaxies, stars, planets, eventually, us. Every spark of the universe traces back to that single moment. Ready to drift further? Let's explore the cosmos together. But first, don't forget to subscribe to this channel. Let's dive in. Right after the Big Bang, something strange happened. The universe didn't just expand, it inflated, like a balloon being blown up in an instant. In less than a fraction of a second, space itself grew unimaginably fast. Not just faster than sound, not just faster than rockets, faster than light. But wait, doesn't physics say nothing can move faster than light? That's true for matter moving through space. But here, it was space itself, stretching. And the laws of relativity don't forbid that. So, the universe ballooned. Tiny quantum fluctuations, microscopic ripples, were stretched across the cosmos. And those tiny ripples became the seeds of everything. Galaxies, stars, planets, life. Without inflation, the universe would look completely different. Maybe no galaxies at all. Maybe just scattered particles, drifting forever. Inflation explains why the universe looks the same in every direction. From our view on Earth, space feels smooth and uniform. The temperature of the cosmic background radiation is nearly identical, no matter where we look. That wouldn't make sense unless the universe had once been stretched beyond imagination. Picture it this way. You bake bread. At first, the dough is tiny, but as it rises, little air bubbles spread evenly throughout. Inflation did something similar. It smoothed out the universe, made it uniform, made it possible for the structure to grow later. But here's the twist. We still don't know what caused inflation. Some scientists think a mysterious field of energy called the inflaton triggered it. Others imagine strange physics beyond anything we've discovered. All we know is that in an instant, the universe expanded by an absurd factor, maybe a trillion times bigger, practically infinite compared to before. And then, just as suddenly, inflation stopped. The energy driving it transformed into particles and radiation. The hot, dense fireball of the early universe was born. That's the Big Bang we usually imagine. But inflation came first. It set the stage. Inflation also leaves behind a cosmic fingerprint. Those quantum ripples, stretched by expansion, left tiny imprints in the microwave background. We can still measure them today with satellites like WMAP and Planck. Little fluctuations in temperature, tiny patterns that map out the birth of galaxies. Proof written into the fabric of the sky. Some scientists even suggest inflation never truly ended. That, in some regions, space keeps inflating forever. That could mean infinite universes, a multiverse, born out of eternal inflation, other realities, other versions of existence. But for us, the important part is this. Inflation explains why we're here at all, why matter clumped together, why galaxies formed, why stars could shine. It was the spark that smoothed chaos into order. In less than a heartbeat, space grew faster than light. And from that, everything else became possible. The early universe was simple. No stars, no galaxies, no planets. Just heat, just light, just energy. But as the universe expanded, it cooled. And when it cooled enough, something incredible happened. Particles began to stick together. First came protons and neutrons, tiny building blocks of matter. At first, they were free, drifting in the hot soup of creation. But soon, gravity and nuclear forces pulled them close. hydrogen was born. The simplest element, one proton, sometimes with a neutron, the most abundant element in the universe. Even today, hydrogen makes up nearly 3/4 of all matter. Not long after helium formed, 2 protons, 2 neutrons, a little more stable, a little heavier. In just the first few minutes after the Big Bang, the recipe of the universe was set. Hydrogen, helium, and traces of lithium. That's it. Those first elements became the foundation for everything else. But here's the fascinating part. All the heavier elements, carbon, oxygen, nitrogen, iron, weren't there at the start. They came later, forged in stars. Every atom in your body, heavier than helium, was cooked in the heart of a star. But hydrogen and helium, they came straight from the beginning. Think about that. Every glass of water, every breath of air, every star in the night sky. They all start with hydrogen and helium. The firstborn children of the universe. Hydrogen is the fuel of stars. It fuses into helium inside their cores. That fusion releases energy. That energy is starlight, and that light makes life possible. Without hydrogen, stars would never shine. Without helium, stars would collapse too quickly. Together, they created stability, balance, a cosmos ready to grow more complex. And it all began just minutes after the Big Bang. This moment is called Big Bang nucleosynthesis, a fancy word for the first creation of atomic nuclei. In that brief window of time, the balance of forces was perfect. Not too hot, not too cold, not too dense, not too thin, just right for protons and neutrons to combine. If the universe had expanded faster, maybe no atoms could form. If it had expanded slower, maybe everything would have collapsed back. But it unfolded at just the right pace, and because of that, matter as we know it could exist. Hydrogen and helium are more than simple gases. They are the alphabet of the cosmos, the first letters written in the story of creation. Every galaxy is built from them. Every star is born from them. Every planet exists because of them. So, the next time you look up at the stars, remember this. The light you see is powered by hydrogen and helium. The air you breathe carries their legacy, and you yourself are made from their descendants. From simplicity came complexity. From 2 simple elements came everything. The universe used to be dark. Not just night sky dark, but thick, impenetrable dark. In the beginning, after the Big Bang, everything was too hot. Particles and light couldn't be separated. Photons, the particles of light, kept bumping into matter, like headlights lost in dense fog. For nearly 380 years, the cosmos was glowing plasma, a soup of electrons, protons, and energy. No light could travel freely, no transparency, no view. But then, the universe cooled. Electrons joined with protons. Atoms formed. Hydrogen, helium. The fog finally cleared, and for the first time, light was free. It stretched across the universe. It traveled in all directions. It became the first light we could ever see. Today, that ancient light is still here. We call it the cosmic microwave background, or CMB. It's faint, it's cold, it's everywhere. The CMB is the afterglow of creation, the baby picture of the universe, not visible to the naked eye. But with special instruments, we can detect it. It looks like a soft glow of microwaves, uniform across the sky, but not perfectly smooth. Tiny ripples exist, and those ripples are important. They are the seeds of galaxies. Little fluctuations in density, slightly more matter here, slightly less there. Over billions of years, those ripples grew. Gravity pulled matter together. Galaxies formed. Stars lit up. Planets spun into orbit, all from faint differences in the CMB. Think about that. The structure of the universe, clusters, voids, filaments, all trace back to tiny variations in that afterglow. The CMB is a map of the universe's childhood. It also tells us about its age, its shape, its destiny. By studying the CMB, scientists discovered the universe is about 13.8 billion years old. They learned space is flat, not curved. They measured how fast it's expanding. The CMB is more than just background noise. It's the cosmic blueprint. And it's still around us today, everywhere, all the time. If your television shows static between channels, a tiny fraction of that fuzz is the CMB. The literal whisper of the Big Bang reaching your screen, the oldest light in existence. The universe doesn't hide its past, it hums with it. It glows with it. It invites us to listen. So when you imagine the universe in its infancy, picture this: a sea of faint microwave light spread evenly in every direction. The afterglow of birth, the first light of freedom, still shining, still waiting for us to look closer. The cosmic microwave background, the soft, faint reminder that everything once began with fire. After the Big Bang, there was fire. After the fire, there was silence. And for a long time, there was only darkness. Astronomers call this era the Cosmic Dark Ages. The universe had cooled. Hydrogen and helium filled the endless space. But nothing shone. No stars. No galaxies. Only blackness. Imagine floating in that young universe. Surrounded by invisible gas. No light to guide you. Only waiting. But hidden inside that gas, change was coming. Gravity was at work. Slowly, patiently, pulling atoms together. Tiny clumps of gas grew denser. Hydrogen gathered. Helium joined in. The clouds thickened, shrinking under their own weight. At first, nothing happened. But deep inside, pressure built. Atoms squeezed tighter and tighter. The center grew hotter. Millions of degrees. Then, something incredible. Hydrogen fused into helium. Nuclear fusion was born. And with fusion came light. The first stars had arrived. They were massive, much bigger than most stars today. Some 100 times larger than our Sunday. Burning hotter, burning brighter. For the first time, the dark universe glowed. These first stars were pioneers. They lit up the cosmic night. They ended the Dark Ages. And they began the age of starlight. But they did more than shine. They created. Inside their fiery hearts, heavier elements were forged. Carbon, oxygen, iron, the ingredients for planets, the ingredients for life. When these giant stars died, they exploded. Supernovas, blasting their elements into space, seeding the universe with the raw material of the future. Every atom in your body traces back to those first stars. The iron in your blood, the calcium in your bones, the oxygen in your lungs, all born in starlight. The first stars also shaped the universe itself. Their powerful radiation pushed away the surrounding gas. It made the universe transparent again. It carved space for galaxies to form. In time, stars gathered into families. Galaxies spun into spirals. Clusters stretched across space. The cosmic web began to take shape. But it all started with those first stars. Think of it this way. The universe had been asleep, silent and dark. Then stars were the alarm clock. They woke the cosmos. They filled it with color. They filled it with life. Billions of years later, their light still travels across space. Some of it may still be reaching us now, a whisper from the very first dawn. So, when you look up at the night sky, remember, you are looking at the legacy of the first stars, the ones that broke the dark, the ones that made everything possible. The universe was once silent, then it began to sing, and its song was made of starlight. The first stars had lit the darkness, but they weren't alone. They were part of something bigger. Gravity doesn't stop once a star is born. It keeps pulling. It gathers stars together. It shapes the universe like an invisible sculptor. In the beginning, stars were scattered, floating far apart in the endless night. But slowly, they began to drift closer. Clouds of gas followed them. Dark matter, an unseen force, added its pull. Imagine drops of water falling on a window. At first, they're small and separate. Then they slide into each other. They merge into something larger. This is how galaxies formed. Billions of stars came together, held tight by gravity. They became great star cities, islands of light in an ocean of space. Some galaxies spun into spirals, like our Milky Way, with graceful arms winding outward. Others became giant glowing balls, elliptical galaxies. Some remained messy and irregular. Each one is unique. But no matter the shape, all galaxies shared one truth. They were homes for stars, homes for planets, homes for everything that was yet to come. Inside them, stars were born in vast clouds of gas. Nebulas, the nurseries of the universe. Young stars burned bright blue. Old stars glowed red. Each galaxy was alive with cosmic generations. And at the heart of most galaxies lurked a secret, a black hole. Not just any black hole, a supermassive one, millions, sometimes billions, of times heavier than the Sunday. Silent, invisible, yet powerful enough to anchor an entire galaxy. Galaxies didn't just stay still, they drifted, they danced, they collided. Sometimes they tore each other apart. Sometimes they merged, creating something new. Even today, galaxies are still on the move. Our own Milky Way is heading toward its neighbor, the Andromeda Galaxy. One day, the two will collide. Two star cities merging into one. Galaxies also shaped the large-scale design of the universe. They gathered in clusters. Clusters linked into superclusters. Together, they formed the cosmic web, vast threads and filaments, stretching across billions of light years. From far away, it looks like a giant map of veins and nerves, the skeleton of the universe itself. And yet, it all began with stars drifting together, gravity whispering, closer, closer. Today, when you look up at the night sky, every tiny dot you see is part of a galaxy. And beyond what you can see, there are trillions more. Galaxies are the grand stage of the cosmos, where stars live, where planets orbit, where life might rise. They are not just collections of stars. They are the cities of the universe, the places where creation builds, grows, and dreams. And in one small corner of one galaxy, a blue planet orbits quietly, wondering how it all began. The Milky Way, our home in the vast universe, a spiral of stars, dust, and mystery. But it wasn't always this way. Long ago, it began small. Tiny clouds of hydrogen, tiny clumps of matter. Slowly, gravity gathered them. Stars were born, clusters formed, and these clusters came together. Piece by piece, they built something larger. The Milky Way grew through mergers. Small galaxies crashed into bigger ones. Their stars were absorbed. Their gas and dust became new fuel. Our galaxy is a survivor of countless cosmic collisions. In the early days, it was messy. No neat spiral, just a rough swarm of stars. But over billions of years, order appeared. A disk began to form. Stars settled into rotation. The spiral arms stretched outward, curling like giant ribbons. At the center, something even stranger formed. A supermassive black hole, 4 million times the mass of our Sunday. Invisible, but powerful. It sits there still, holding the galaxy together. Around it, billions of stars spin. Young blue stars shine in the spiral arms. Old red stars gather in the bulge near the center. Dust clouds weave through the disk like rivers of shadow. Our solar system arrived late to the party, about 4.5 billion years ago, born in one of the spiral arms, far from the center, close enough to other stars to be part of the galaxy, but far enough to avoid danger. The Milky Way didn't stop growing. It still eats smaller galaxies today. Right now, it's pulling apart the Sagittarius dwarf galaxy, piece by piece, star by star, adding it to its own collection. And, in the far future, an even greater event awaits. The Andromeda Galaxy is on a slow collision course. Billions of years from now, the two galaxies will merge. The Milky Way will change forever. A new galaxy will be born. Some call it Milkomeda. For now, though, the Milky Way is steady. A grand spiral, stretching 100 light-years across, home to hundreds of billions of stars, and maybe even more planets, perhaps trillions. Every star you see in the night sky belongs to it. Every constellation, every familiar point of light. It's all part of this one galaxy. But beyond it, there are billions more, each with its own story, each with its own mysteries. Still, the Milky Way is special because it is home. It is the stage where Earth was born, where life rose, where humans looked up and wondered. Our galaxy is not just a place, it is our origin, our cosmic family, and one day it will also be our future. Black holes. The name alone feels heavy, mysterious, almost frightening. But what are they, really? They are the universe's most extreme children of gravity, born when stars die. Imagine a star much bigger than our Sunday. It burns bright for millions of years, but one day it runs out of fuel. No more nuclear fire to push back against gravity. The core collapses. The star falls in on itself. The weight is unbearable, and in an instant, a black hole forms. A place where gravity wins completely, where escape is impossible. Not even light can get out. That's why they're called black holes. At the center is what scientists call a singularity, an unimaginable point. All the mass was crushed into something infinitely small. Physics as we know it breaks down. We don't know what truly happens there. Surrounding it is the event horizon, a one-way boundary. Cross it and you're gone, forever. From the outside, time itself seems to stop at that edge. Inside, the story ends. But black holes are not just destroyers. They shape the universe. Some are small, just a few times the mass of the Sunday. Others are monsters, millions or even billions of times heavier. These giants sit at the hearts of galaxies, including our Milky Way. And though we can't see them directly, we see their effects. Stars whip around them at incredible speeds. Gas and dust fall inward, heating up. Before vanishing, they shine with more energy than entire galaxies. That's how quasars are born. Black holes also bend space and time, like bowling balls on a trampoline, but far stronger. They warp light. They twist reality. They remind us that the universe is stranger than imagination. Even stranger, black holes may not last forever. Stephen Hawking suggested they slowly evaporate. Bit by bit, particle by particle. It would take trillions of years. But even the darkest hole might someday vanish. For now, though, they remain, silent, hidden, waiting in the dark. Every galaxy has them. Every corner of the cosmos is shaped by them, and one day our galaxy will collide with another. The black holes at their centers will meet. They will spiral together, merge, and create an even bigger one. Black holes are extreme, but they are also natural. They are the universe's way of recycling matter. Stars die, black holes are born, and galaxies evolve. When you look at the night sky, remember this. Behind the stars, behind the beauty, there are invisible giants, silent guardians, the most mysterious engines of creation and destruction. Black holes, gravity's masterpiece. Let's talk about something you can't see, something that doesn't shine, doesn't glow, and doesn't reflect light. And yet, it holds the universe together. Dark matter. It makes up most of the matter in the cosmos. But here's the twist. We don't actually know what it island. Astronomers first noticed the mystery when they looked at galaxies. Stars were moving too fast. If only visible matter were there, planets, stars, gas clouds, galaxies should have torn themselves apart. The math didn't add up. Something invisible was keeping them whole. That something is dark matter. It doesn't interact with light. That's why telescopes can't see it. But we know it's real because of its gravity. Think of dark matter as an invisible web. Galaxies are caught in it, held in place. Without it, stars would scatter into space. With it, galaxies spin safely for billions of years. Even larger structures, clusters of galaxies, depend on it. Dark matter forms a cosmic skeleton, an unseen framework that shaped the universe after the Big Bang. Gas and stars collected where dark matter was thick. Galaxies formed along those hidden lines. Without dark matter, the night sky would be empty. So what is it made of? That's the puzzle. It's not atoms like you and me. It's not the stuff of planets, clouds, or stars. Scientists think it could be strange particles we haven't discovered yet. Names like WIMPs or axions float around, but so far, no one has caught one. We've built giant detectors deep underground. We've sent telescopes scanning the skies. Still, dark matter remains hidden, silent, untouchable, and yet its fingerprints are everywhere. We see it in the way galaxies rotate. We see it bending light from distant galaxies, a trick called gravitational lensing. It acts like a magnifying glass, warping space itself. Dark matter is the reason the universe looks the way it does. It shaped the first galaxies. It still guides their growth. And even though we can't see it, we live inside it. The Milky Way swims in a vast halo of dark matter. It surrounds us like an invisible ocean. Here's the humbling part. All the stars, planets, gas, and dust, everything we can see, is just a small slice of reality. Ordinary matter is less than 5% of the universe. Dark matter makes up about 27%. The rest? That's something even stranger, dark energy. But that's a story for another section. For now, remember this. The cosmos has bones, a hidden skeleton that keeps it standing tall. And even if we can't touch it or see it, we know it's there, because without it, we wouldn't be here at all. Dark matter, the invisible glue of everything. The universe isn't just expanding, it's speeding up. That fact alone shocked astronomers. For decades, scientists thought gravity would slow the expansion down. After all, every galaxy, every star, every planet has mass, and mass pulls things together. So, the universe should have been stretching more slowly over time. But in the 1990s, two teams of astronomers looked at distant supernovae exploding stars. These cosmic explosions are like reliable beacons. They let us measure distances across billions of light years. What the teams found was stunning. The light from faraway supernovae was dimmer than expected. That meant they were farther away than they should have been. And that could only mean one thing. The expansion of the universe is not slowing down. It's accelerating. Something is pushing the universe apart. That something is what we call dark energy. Like dark matter, we can't see it or touch it, but we know it's there because of its effect. Dark energy is everywhere. It fills all of the space, and the more space expands, the more dark energy we get. It works against gravity. Gravity pulls matter together. Dark energy pushes everything apart. The two forces are locked in a cosmic tug-of-war. For billions of years after the Big Bang, gravity was stronger. Galaxies formed, stars lit up, planets appeared. But then, around 5 billion years ago, the balance shifted. Dark energy took over, and expansion began to accelerate. Today, dark energy makes up about 68% of the universe, more than 2/3 of everything. Yet, we know almost nothing about it. What is it? That's the big question. One idea is that it's a property of space itself. Empty space isn't truly empty. It has energy built in. As space grows, more of this energy appears, and that energy acts like a repulsive force. Another idea, maybe dark energy is a new kind of field, something dynamic, shifting, evolving with time, a hidden energy woven into the very fabric of reality. Or perhaps our understanding of gravity is incomplete. Einstein's equations might not tell the full story. Maybe, on the largest scales, gravity behaves differently than we think. Whatever it is, dark energy is shaping the future of the cosmos. If it stays constant, the universe will keep expanding faster and faster. Galaxies will drift apart. Distant stars will vanish from view. The night sky will grow darker and emptier. If dark energy grows stronger, it could rip galaxies, stars, and even atoms apart. A fate called the Big Rip. And if it weakens or reverses, gravity might win again. The universe could slow, stop, and collapse back in a big crunch. No one knows which path lies ahead, but one thing is certain: dark energy is the most powerful and mysterious force in the cosmos. It doesn't just shape space, it shapes destiny. Every star has a story, and like us, stars are born, they live, and they eventually die. But their lives unfold on timescales far beyond human imagination. It all begins inside vast clouds of gas and dust. We call them nebulae. These are the nurseries of the cosmos, cold, dark, and enormous, stretching across light years. Inside a nebula, gravity slowly pulls matter together. Tiny clumps form. Then, those clumps attract more gas. Bit by bit, the material gathers into a growing ball. This ball of gas is the seed of a star. As it shrinks, the gas heats up. Pressure builds at the core. Temperatures climb to millions of degrees. At this point, the young star is called a protostar. Protostars don't shine like normal stars yet. They glow faintly from the heat. They're unstable, surrounded by disks of gas and dust. And sometimes, they shoot out jets of material into space. They are stars in the making, still under construction. But something dramatic is waiting to happen inside. When the core gets hot and dense enough, hydrogen atoms begin to fuse. Hydrogen turns into helium. This process releases enormous amounts of energy, and for the first time, the star truly shines. This moment is the star's ignition, the start of its real life. The star now enters its longest phase, the main sequence. Here, it finds balance. Gravity is pulling everything inward, but the energy from fusion pushes outward. The two forces cancel out, and the star becomes stable. Our sun is in this phase right now. It has been for 4.6 billion years, and it will stay here for billions more. The main sequence is when stars live out most of their lives. Small stars, called red dwarfs, can last for trillions of years. They burn their fuel slowly, living quiet and steady lives. Big stars live fast and die young. They burn brighter, hotter, and use up their fuel in just a few million years. But while they last, they dominate their galaxies. They create the heavy elements that will one day form planets and maybe life. The life of a star is a balance of forces. Gravity is trying to crush it. Fusion is fighting to push outward. And, as long as fusion continues, the star endures. Eventually, though, the fuel runs out. And that's when the story takes a darker turn. But for now, in this phase, stars shine steadily. They light up galaxies. They heat planets. They provide the conditions for life. From a quiet nebula to a blazing main sequence star, the journey is both violent and beautiful. Every star you see in the night sky has lived through this story, and every one of them began as a whisper in the dark, a nebula waiting to shine. Not all stars die in violent explosions. Some stars, like our sun, take a quieter path. Their ending is gentle compared to the supernova fireworks of massive stars. Here's how it unfolds. A star spends most of its life in the main sequence, burning hydrogen into helium. But eventually, the hydrogen fuel in the core runs out. Fusion slows. Gravity starts winning the tug of war. The core shrinks and heats up. Something dramatic happens in the outer layers. They swell outward. The star grows enormously. hundreds of times its original size. It becomes a red giant. Our Sun will go through this stage about 5 billion years from now. When it does, it will expand so much that it could engulf Mercury and Venus. Earth's fate is uncertain, but life, as we know it, will be long gone. A red giant is cooler on the outside, which is why it glows with a reddish tint. But inside, the core is hotter than ever. Here, helium atoms fuse into carbon and oxygen. The star keeps shining, but it's unstable. Its outer layers drift away into space, forming a glowing shell of gas called a planetary nebula. These nebulae are breathtaking. Like cosmic lanterns, they light up the galaxy. But they are short-lived, lasting only tens of thousands of years. Eventually, the nebula fades. What remains at the center is small, dense, and incredibly hot. This is the star's final form, a white dwarf. A white dwarf is tiny, about the size of Earth, yet it contains the mass of the Sunday. Its matter is packed so tightly that a teaspoon of it would weigh tons. There's no fusion happening anymore. It shines only from leftover heat. Over billions of years, it slowly cools and dims. One day, it will become a cold, dark remnant called a black dwarf. But the universe isn't old enough for any black dwarfs to exist yet. Every white dwarf we see is still glowing faintly in the night. This quiet end is very different from the chaos of a supernova. No violent explosion, no shockwave ripping through the galaxy, just a steady fade into darkness. Yet, even in this gentle death, the star leaves a gift. The gas and dust it sheds enrich the galaxy. That material, carbon, oxygen, and more, becomes part of new stars, new planets, and maybe even new life. So, when you look at a white dwarf through a telescope, you're seeing the afterglow of a star's long journey, a peaceful conclusion to billions of years of shining, a reminder that not every ending needs to be violent. Our Sun is destined for this path. It will one day become a red giant, then leave behind a glowing planetary nebula, and finally shrink into a white dwarf. And long after we are gone, it will still be there quietly cooling, silently shining. Some stars don't go quietly. They don't fade into white dwarfs. They end their lives in spectacular explosions called supernovae. A supernova is one of the most powerful events in the universe. For a short time, a single star can outshine an entire galaxy. That's how bright these cosmic fireworks are. So, how does it happen? Massive stars, much bigger than our Sun, burn through their fuel quickly. They fuse hydrogen into helium, helium into carbon, carbon into heavier and heavier elements. But eventually, they hit a wall. They start producing iron in their core. And here's the problem. Iron doesn't release energy when it fuses. Fusion stalls. The delicate balance between gravity and pressure collapses. The core of the star caves in on itself in a fraction of a second. Temperatures skyrocket. The outer layers crash inward, then rebound in a colossal blast. This is the supernova explosion. It's violent, it's destructive, but it's also creative. That titanic explosion forges the heavy elements: gold, silver, uranium, and more. Everything heavier than iron comes from these cosmic deaths. Without supernovae, there would be no planets, no oceans, no bones in our bodies. The calcium in your teeth, the iron in your blood, the gold in your ring, all made in the heart of a dying star. Supernovae also play another vital role. They spread those new elements out into space. The shockwave blasts material far and wide, seeding galaxies with the ingredients for the next generation of stars and planets. In a way, every supernova is both an ending and a beginning. Astronomers have even seen these explosions in real time. In 1987, a star in the Large Magellanic Cloud went supernova. It was bright enough to see without a telescope. Since then, telescopes like Hubble have captured stunning images of supernova remnants, glowing clouds of gas shaped by shockwaves. These remnants are hauntingly beautiful. They're like cosmic tombstones, marking where a giant once lived. But they're also nurseries, because new stars often form in the rich material left behind. There's another twist. Sometimes, the collapsed core of a massive star becomes a neutron star, a city-sized ball of pure neutrons. Spin it fast, and you get a pulsar, flashing beams of light across the cosmos. And if the star was truly gigantic, the collapse doesn't stop, it keeps going, forming a black hole. So, from one explosion, we get new elements, new stars, and some of the most exotic objects in the universe. Supernovae remind us of a simple truth. Destruction and creation are two sides of the same coin. From stellar death comes cosmic rebirth. And here's the most poetic part: without these cataclysms, you and I wouldn't exist. We are literally made of star stuff. So next time you see the night sky, remember, every sparkle is a survivor of billions of years of stellar drama. And somewhere out there, another star is preparing for its final spectacular act. If you're fascinated by stories like this, make sure to subscribe so you don't miss the next cosmic mystery. When a massive star explodes as a supernova, something strange is left behind. Not a planet, not another Sunday, but one of the weirdest objects in the universe. A neutron star. Let's break it down. In the chaos of the explosion, the star's core collapses. Gravity crushes atoms so tightly that protons and electrons merge. They fuse into neutrons. The entire core becomes one giant ball of neutrons. How dense is it? Unimaginably dense. A teaspoon of neutron star material would weigh about 1 billion tons. Yes, just one spoonful. Now imagine something only about 20 kilometers wide. That's smaller than most cities, but it has more mass than our entire Sunday. That's a neutron star. The surface is no place you'd want to visit. Gravity is so intense it would squash you instantly. Mountains, if they exist, rise only a few millimeters high. The crust is harder than any material on Earth. And neutron stars don't just sit there quietly. They spin fast. Some rotate dozens, even hundreds of times per second. As they spin, they shoot out beams of radiation. These are called pulsars, cosmic lighthouses, flashing across the galaxy. Astronomers first discovered pulsars in the 1960s. At first, they thought the signals were from aliens. The pulses were so regular, so precise, like the ticking of a clock. But no, it was a neutron star announcing its presence. Some neutron stars are even stranger. They have magnetic fields billions of times stronger than Earth's. We call these magnetars. Their magnetic forces can rip apart atoms and cause bursts of energy so powerful that they can be seen across galaxies. So, what happens if two neutron stars collide? Another fireworks show. The impact shakes the very fabric of space-time, creating gravitational waves. It also forges some of the heaviest elements in the universe, like gold and platinum. That ring on your finger? It might have been born in the crash of two neutron stars. Neutron stars are reminders of how extreme the universe can be. Stars that once shone with light and warmth collapse into these tiny, terrifying corpses. They're small but mighty, dead but still full of energy. And the next time you look up at the night sky, remember, somewhere out there, a neutron star is spinning, fast, silent, dense beyond imagination. One of the strangest survivors of a star's violent death. Some stars don't go quietly. They don't fade into white dwarfs. They don't stop at neutron stars. They go further. They collapse into the most terrifying objects in the universe. Black holes. Here's how it happens. Take a star much bigger than our Sunday. It burns for millions of years. It fuses hydrogen into helium into heavier elements, until it builds iron at its core. But iron is a problem. It can't release energy through fusion. It's like the star hits a brick wall. No more fuel, no more balance. Gravity takes over. The core collapses. In seconds, the star shrinks to almost nothing. Outer layers blast out as a supernova. The core, it keeps falling. falling, falling, until nothing can stop it. What's left is a singularity, a point of infinite density, surrounded by an invisible boundary called the event horizon. Cross that horizon and you're gone, forever. Not even light can escape. That's why it's called a black hole. The numbers are wild. Imagine a star many times bigger than our Sunday. Now, imagine squeezing that mass into something smaller than a city. The result? Gravity is so strong that it warps space and time. What would it look like? You wouldn't see the hole itself. It's black, but you'd see what it does to its surroundings. Matter falling in forms a swirling disk. Gas heats up. It glows. X-rays shoot out. The black hole feeds, and the galaxy watches. Some black holes spin faster than you'd believe. Their rotation drags space around them like a whirlpool. Others launch giant jets of energy that stretch across galaxies. Beams so powerful they outshine entire star systems. Here's the scary part. Time behaves differently near a black hole. Get close, and time for you slows down compared to the outside universe. To you, only minutes might pass. To others, millions of years. Black holes don't just bend space, they bend reality itself. And yet, they're not just destroyers. They play a role in shaping galaxies. At the heart of most galaxies, including our Milky Way, sits a supermassive black hole. Millions, even billions of solar masses. Without them, galaxies might never have formed the way they did. So, black holes are both monsters and architects. They devour, but they also create structure in the cosmos. It's the ultimate paradox. The darkest objects in the universe are also some of the most important, the wrecks. When a massive star collapses, it doesn't just die, it transforms into a black hole, into pure mystery, into a reminder that the universe always has one more trick up its sleeve. Galaxies look peaceful from far away, beautiful spirals, gentle clouds of stars. But that's an illusion, because galaxies crash, they collide, they tear each other apart, and it's happening all the time. Picture 2 giant star cities. Each has hundreds of billions of stars. Gas, dust, dark matter halos surrounding them. Now, imagine them drifting closer. Gravity takes over. The dance begins. But here's the twist. Stars almost never hit each other. Why? Because the space between stars is massive. When galaxies collide, it's not stars smashing head-on. It's gravity pulling everything into new orbits. A slow-motion cosmic ballet. Gas clouds slam together. Shock waves ignite. New stars are born. Some galaxies burst with light during these encounters. Others stretch into strange shapes, tails, bridges, and loops of stars flung into space. It's not quick. A galactic collision takes hundreds of millions of years. To us, it's unthinkably slow. But to the universe, it's just another heartbeat. Our own galaxy, the Milky Way, is on this path. Right now, we're heading toward our neighbour, the Andromeda Galaxy. In about 4 billion years, the two will meet. It won't be a fiery explosion. It'll be a long, slow embrace. Spirals twisting, stars shifting, until both galaxies merge into one giant elliptical galaxy. Some call it Milkomeda. So, what happens to Earth when this collision begins? Astronomers say the odds of our Sun colliding with another star are tiny, but our sky will change. We'd see Andromeda growing bigger and brighter. Eventually, the heavens will glow with streams of stars arcing across the sky. It'll be beautiful and terrifying. Galactic collisions shape the universe we see today. Some of the biggest galaxies, those giants at the centers of clusters, are the result of countless mergers. Every time galaxies collide, they grow, they evolve, they become something new. Even black holes get in on the action. When galaxies merge, their central supermassive black holes spiral toward each other. Eventually, they collide too, releasing gravitational waves, ripples, in space-time itself. We can detect those waves today, Proof that galaxies don't just sit still. They move, they fight, they transform. So galactic collisions aren't cosmic accidents. They're part of the story, part of how the universe builds bigger, more complex structures. When galaxies crash, destruction and creation go hand in hand. Old shapes are lost, new ones rise. It's the universe at its most dramatic, rewriting itself with every encounter. One day, our galaxy will merge too. We'll be part of a new creation. The Milky Way won't survive. But its stars, its planets, its history, they'll live on in something larger. Galactic collisions are the universe reminding us of one truth. Even the biggest things are never permanent. Change is the only constant. Look up at the night sky. Beyond the stars, beyond the faint glow of the Milky Way, there's another galaxy. The Andromeda Galaxy, 2.5 million light-years away. It looks calm, silent, but it's on a crash course with us. That's right. Our Milky Way and Andromeda are destined to collide. It's not a maybe. It's written in the math. The pull of gravity has locked our galaxies into a slow-motion embrace. And in about 4 billion years, they'll meet. So, what will happen? First, Andromeda will grow larger in our sky. Brighter, more detailed. Imagine it stretching across the heavens like a glowing arch of stars. Astronomers say the view will be breathtaking. The night won't be dark anymore. It'll be alive with rivers of light. Then the real dance begins. The galaxies will pass through each other, spirals twisted, stars tugged into long tails, clouds of gas slamming together. A storm of new stars will ignite. Whole regions of space will glow with fresh energy. But here's the surprise. Even though galaxies collide, stars almost never smash into each other. Why? Because space is mostly empty. The sun will keep shining. Earth will keep orbiting. But our position in the galaxy may shift. We could be flung into a new orbit, or even drift further out into space. Over billions of years, the Milky Way and Andromeda will pass through each other again and again. Gravity is reshaping both, until they finally merge. What's left won't be a spiral galaxy anymore. It'll be a giant elliptical galaxy. Astronomers call it Milkomeda. At its heart, something even bigger will happen. The supermassive black holes at the centers of both galaxies will spiral together. They'll collide, and when they do, they'll release a storm of gravitational waves, ripples in space-time itself. The universe will shudder. So, what does this mean for us? By the time this galactic collision happens, Earth will already be in trouble. The sun will be older and hotter. Life here might not even exist anymore, but if it does, the view will be extraordinary. A sky filled with two galaxies twisting into one. A light show on a cosmic scale. This is the fate of the Milky Way. Not destruction, transformation, from a spiral to a giant elliptical, from one galaxy to something greater. Andromeda is coming. We can't stop it, but we don't need to fear it. This is how the universe grows, how it evolves, how it creates beauty out of chaos. In the end, our galaxy won't be lost. It'll live on inside something bigger, something new. The future of the Milky Way is not an ending, it's a beginning. Let's rewind 4.5 billion years ago, before Earth. Before the sun had planets, there was only dust. A vast cloud of gas and dust floated in space, cold, silent, leftovers from stars that had exploded long before. This cloud was called a nebula. Then, something happened. A shockwave, maybe from a nearby supernova, disturbed it. The cloud started to collapse under its own gravity, and at the very center, matter piled up. It got hotter, denser, until it lit. Our sun was born. But the story doesn't end there. Around the young sun, the leftover gas and dust spun into a giant disk, a cosmic pancake. Inside that disk, particles began to stick together, grain by grain, pebbles, then rocks, then massive chunks called planetesimals. Collisions were everywhere. Not gentle bumps, violent impacts. Worlds smashing into worlds. Some shattered. Some grew. The winners became the planets. Closer to the sun, it was too hot for ice to survive. So the inner planets Mercury, Venus, Earth, Mars formed from rock and metal. Small, dense, solid, the building blocks of terrestrial worlds. Farther out, where it was colder, ice could stay frozen. Here, giant planets grew. Jupiter, Saturn, Uranus, Neptune. They captured huge amounts of gas, becoming the massive worlds we see today. Jupiter especially shaped everything. Its gravity hurled smaller bodies around like toys. Some were flung out of the solar system forever. Others smashed into young planets, delivering water, metals, and organic molecules. Chaos built order. And Earth? It wasn't peaceful. A giant object the size of Mars slammed into it. The impact blasted molten rock into orbit. That debris came together and formed our moon. A scar from a cosmic collision, but also a blessing. The moon stabilizes Earth's tilt. It gave us tides. It helped life flourish. Over millions of years, the violence settled. The sun burned steadily. Planets cleared their orbits of debris. Asteroids and comets remained as leftovers, frozen time capsules of that ancient era. And slowly, Earth cooled. Water gathered. The atmosphere thickened. Conditions for life began to take shape. Our solar system, from dust to planets, was complete. Not in a day, not in a year, but over hundreds of millions of years. A masterpiece carved by gravity. And what's incredible? This same process happens across the universe. Stars forming, disks spinning, planets are coming together. Other solar systems are being born. Right now, we are the children of dust. Everything, our oceans, our mountains, even us, was once floating in a cloud of gas. Stardust sculpted by time, chance, and collisions. That's the origin of our home. The story of how dust became planets, and how nothing turned into everything we know. Picture this, 4.5 billion years ago. Earth was not blue, not green, not peaceful. It was a ball of fire, a molten world, red-hot rock bubbling like lava across its surface, mountains of liquid magma, seas of boiling stone, no oceans, no sky, no life. The young sun blazed above, still fierce from its birth, and all around, the solar system was in chaos. Asteroids, comets, leftover chunks of rock and ice, all smashing into Earth, over and over. Each impact melted the surface again. Each collision brought heat, metal, and sometimes water. The biggest hit of all? The Mars-sized body that slammed into Earth. That colossal impact tore off a huge chunk of Earth's crust. Debris spun into orbit and slowly came together. That's how the moon was born. Our eternal companion, forged in violence. But back on Earth, things were brutal. The air was thick with poisonous gases, carbon dioxide, methane, ammonia. The sky glowed orange from volcanic eruptions. Lightning flashed constantly through the haze. A toxic, stormy atmosphere. And the ground beneath? Still molten, still shifting. But slowly, change began. The planet started to cool. Not everywhere, but enough for the first crust to harden. Dark rock floated on seas of magma. Land was fragile, easily broken, but it was a beginning. Volcanoes belched gases that built a new atmosphere. And when comets bombarded Earth, they delivered something precious: water. Over millions of years, vapor in the skies condensed. Clouds formed. Rain fell, not gentle showers, endless storms. The rains lasted for thousands, maybe millions of years, filling basins, carving valleys, creating the first oceans. But imagine those oceans. They weren't calm blue seas. They boiled with heat. They steamed under the Sunday, and yet they were the first real sign that Earth could transform. From fire to water, from chaos to balance, the young planet was still restless. Tectonic plates shifted, continents cracked and drifted. The moon's pull stirred tides, keeping Earth's rotation steady. Every detail mattered. Every force shaped the world we know today. From molten beginnings, Earth was slowly becoming something more. Still harsh, still deadly, but no longer just a ball of fire. It had land, it had water, it had an atmosphere. The stage was set, the foundation laid. Life wasn't here yet, but the conditions were forming. The right mix of rock, water, air, and energy. All born out of fire and fury. That's the birth of Earth. Not gentle, not quiet, but violent, explosive, magnificent. We walk today on a planet that was once unrecognizable, a reminder that beauty often begins in chaos, and that even a molten world can cool into a home. Look up at the night sky. The moon feels calm, peaceful, silent, but its origin? Anything but peaceful. 4.5 billion years ago, Earth was young, still molten, still under attack from the leftover debris of the solar system. Then it happened. The impact that changed everything. A planet-sized body, roughly the size of Mars. We call it Theia. It slammed into Earth, not a gentle collision, a cosmic catastrophe. The explosion released unimaginable energy, enough to melt rock, enough to shake the planet to its core. Earth's outer layers were blasted into space. Molten rock, vaporized metal, an orbiting cloud of fire and dust surrounded the planet. This wasn't a few fragments. It was billions of tons of material. A glowing ring of debris. Gravity went to work. Pieces clumped together. Collisions welded rock to rock. In weeks, months, maybe years, the debris began to gather. Slowly, a new body took shape. Round, massive, our moon was born. But this wasn't the end of the story. The moon began much closer to Earth. So close, it looked enormous in the sky. Its pull created giant tides. Tides that shook the oceans. Tides that slowed Earth's rapid spin. Back then, Earth spun once every 5 or 6 hours. The moon's gravity stretched that day longer and longer. And still today, the moon pulls, adding tiny fractions of time. Our 24-hour day? Thank the moon. It also stabilized Earth's tilt. Without it, our axis would wobble wildly. Seasons would swing out of control. Climate would lurch from frozen to scorching. Life as we know it might never have stood a chance. But the moon's influence didn't stop there. Its tides stirred the early oceans. They created pools along rocky shores, places where water is concentrated, where chemistry had time to work, where life could spark. The moon, born in violence, became a guardian, a partner, a stabilizer. And think about this. That catastrophic collision, it destroyed Theia. It nearly destroyed Earth. But it gave us the moon, and that moon shaped the conditions for life. Every time you see it glowing, remember this. It's not just a dead rock. It's the scar of a colossal impact, the survivor of a cosmic battle, the reason our planet is steady, the reason life had a chance to rise. From chaos, balance was born. From destruction, creation followed. The moon's calm face hides its violent birth. But without that story, we wouldn't be here to tell it. Take a deep breath. Feels good, right? Fresh air. Oxygen keeps you alive. But rewind the clock. 4 billion years ago, breathing would kill you. Back then, Earth's atmosphere was nothing like today. No blue skies, no fluffy clouds, no oxygen at all. Instead, the air was poisoned. Thick, heavy, toxic. What filled it? Carbon dioxide, nitrogen, ammonia, methane, traces of sulfur gases from endless volcanoes. Imagine the smell. Rotten eggs, burnt metal, the stench of a restless planet. Lightning cracked through choking clouds. Meteors rained down. Volcanoes blasted fire into the sky. The air shimmered with deadly chemicals. The surface, scorching hot. The seas boiled with dissolved gases. Rain fell, but it was acidic. No creature like us could have survived. And yet this atmosphere wasn't useless. It set the stage. It was raw chemistry waiting to be stirred. Ammonia and methane. Lightning is a spark. Oceans are the mixing bowl. Together, they brewed the first complex molecules. The building blocks of life. This poisonous sky was a laboratory, a dangerous one, but it was working on something incredible. Now, here's the strange part. For nearly 2 billion years, Earth had no oxygen. Life did exist, but it was tiny, simple microbes, and they didn't breathe oxygen. They thrived in the poison. Then came the great shift. Cyanobacteria, tiny blue-green algae. They evolved photosynthesis. Using sunlight, they split water. They released a waste gas. That waste gas? Oxygen. At first, oxygen didn't build up. It was swallowed by the oceans. It rusted iron on the seafloor. The oceans turned red from oxidized iron. But slowly, oxygen filled the air. The great oxidation event had begun. It poisoned the old life. Many microbes died, but new possibilities opened. Breathing oxygen gave more energy. Complex life could evolve, but never forget where it began. Before oxygen, before blue skies, Earth's air was a death trap, a toxic blanket that choked the surface. And yet, from that poison came progress. From deadly skies came the chemistry of life. Without that hostile start, we might not exist. So, the next time you take a breath, think of this. You're inhaling a gift forged by billions of years of change, a gift born from skies that once could kill you. Earth's first atmosphere was poisonous, but it paved the way for oxygen, and oxygen paved the way for us. Take a deep breath. Oxygen fills your lungs. You don't even think about it. But there was a time when Earth had almost none. The story starts with tiny creatures. Cyanobacteria, little blue-green algae, are floating in the oceans. They looked simple, microscopic specks, but they had a secret weapon: photosynthesis. Using sunlight, they split water, they made sugar, and as waste, they released oxygen. At first, that oxygen vanished. Rusted iron dissolved in the oceans. The sea floor turned red, covered in iron oxide. Bands of rust layered the rocks forever. For millions of years, the oxygen kept disappearing. The oceans swallowed it. The land absorbed it. But cyanobacteria didn't stop. They kept pumping oxygen out. And then it happened. Around 2.4 billion years ago, the sinks were full. The iron was rusted. The rocks were saturated. Oxygen had nowhere left to go. So it began to build up in the air. The great oxidation event had begun. For the first time, Earth's skies turned blue. Ozone is formed in the upper atmosphere. The poisonous blanket of methane and ammonia thinned. Daylight looked different. The planet felt different. But not everyone celebrated. For the microbes used to a toxic, oxygen-free world, this was a disaster. Oxygen was poison to them. It burned their cells. It destroyed their chemistry. Mass death followed. One of Earth's first great extinctions. But with extinction came opportunity. Some life adapted. Some learned to use oxygen instead of fearing it. Breathing oxygen gave them more energy. They could grow bigger. They could become more complex. The great oxidation event wasn't just a change in the air. It was a revolution. It transformed Earth from a world of microbes into a world with the potential for animals, plants, and eventually us. It also reshaped the environment. The ozone layer blocked deadly ultraviolet rays. Land became safer. Life could leave the ocean someday. And the chemistry of Earth changed too. Oceans altered. Minerals shifted. New ecosystems were born. The great oxidation event is one of the most important turning points in history. It shows how life can transform a planet. Tiny microbes, barely visible, reshaped the atmosphere forever. Think about that. The air you breathe is a gift from ancient bacteria. Every breath is a reminder of their work. Without them, no forests, no animals, no people. The Great Oxidation Event was violent. It was deadly, but it was also creative. It gave Earth the oxygen-rich world we know today. Life didn't just adapt to the planet. Life changed the planet. And in that moment, Earth became something new. A world where life and air were forever linked. Picture the Earth 540 million years ago. The oceans ruled everything. No forests, no grass, no animals walk on land. Just water, stretching as far as you could imagine. And in those oceans, something extraordinary was about to happen. Life was about to explode. Not an explosion of fire, an explosion of diversity. The Cambrian explosion. Before this moment, Earth was quiet. For billions of years, microbes, algae, and a few simple multicellular creatures lived in the seas. Sponges, worm-like forms, nothing too complex. The planet looked empty compared to today. Then suddenly, around 541 million years ago, life went wild. New body plans appeared almost overnight in geological time. Creatures with shells, creatures with eyes, creatures that could swim, burrow, and hunt. Predators arrived. Prey evolved defenses. It was an arms race written in biology. Trilobites crawled across the seafloor. Worms tunneled in the mud. Strange forms like hallucigenia with spikes and legs looked like creatures from a dream. And then there were the monsters of the seas, like Anomalocaris with grasping claws and a circular mouth. For the first time, ecosystems formed. Food chains developed. Life was no longer just floating and feeding passively. It was competing. It was fighting. It was evolving faster than ever. What caused this sudden burst? Scientists debate it even now. Maybe oxygen levels rose high enough to support more active creatures. Maybe changes in the chemistry of the oceans opened new doors. Or maybe genetic innovations, like the rise of Hox genes, gave organisms the toolkit to build complex bodies. Whatever the trigger, the result was clear. In a relatively short span, nearly all the major groups of animals we know today appeared. Arthropods, mollusks, chordates, the group that would one day include us. The Cambrian explosion was like nature's big experiment. Some designs lasted, others vanished forever, but the blueprint of life as we know it was written here. This wasn't just more species. It was complexity, movement, interaction, the foundations of modern ecosystems. The ocean floors went from quiet to bustling. A world once ruled by bacteria turned into one ruled by creatures with shells, claws, and teeth. It was the dawn of animals. And the best part, we can still see its legacy today. Fossils in places like the Burgess Shale in Canada capture these creatures in stunning detail. Every fossil tells the story of that wild, creative burst of evolution. Without the Cambrian explosion, life might still be simple. No fish, no forests, no humans. It was one of evolution's greatest turning points. The moment the ocean came alive, and the stage was set for the long, wild journey of life on Earth. Life on Earth has always been fragile. It grows, it flourishes, and sometimes it nearly ends. We call these moments mass extinctions. They're like hitting the reset button on the planet's story. Not small losses, not a few unlucky species, but massive die-offs that wipe out most life in a geological blink. 5 major ones have scarred Earth's history. Let's walk through them. The first happened about 444 million years ago, the Ordovician extinction. Life then was mostly in the oceans. Ice sheets grew, sea levels dropped. Nearly 85% of marine species vanished. The oceans became graveyards. Then came the Devonian extinction, around 375 million years ago, sometimes called the Age of Fishes. but oxygen levels dropped in the seas. Coral reefs collapsed. Fish diversity plummeted. It wasn't as sudden, but it dragged on for millions of years. The third one was the Permian extinction, the Great Dying. About 252 million years ago, this was Earth's darkest hour. Volcanoes erupted for ages, pumping carbon dioxide into the skies. Temperatures soared. Oceans turned acidic. Methane might have been released from the seafloor. Result? Over 90% of species are gone. Almost everything. Trilobites, which had ruled for hundreds of millions of years, disappeared forever. It was as close as life has come to ending. But life crawled back. It always does. Next was the Triassic extinction, about 201 million years ago. Volcanoes again. Climate chaos again. This one cleared the way for the rise of the dinosaurs. From tragedy came opportunity. And then, the most famous. The Cretaceous extinction occurred 66 million years ago. An asteroid struck what is now Mexico. The impact was devastating. Firestorms. Dust clouds are blocking sunlight. Temperatures plummeted. Dinosaurs, except for the ancestors of birds, vanished. Mammals, once small and overlooked, suddenly had room to grow. That opening, eventually, led to us. 5 great extinctions. Each one a turning point. Each one rewriting life's script. And here's the thing, extinction is not just ancient history. Scientists believe we may be living through a 6th mass extinction right now. Not from asteroids, not from volcanoes, but from human activity, habitat loss, pollution, climate change. Species are vanishing at rates far above normal. The reset button may be hovering again. Mass extinctions remind us of 2 truths. 1, life is fragile. 2, life is resilient. After every collapse, it bounces back. Different, changed, but alive. Without them, we wouldn't be here. The death of the dinosaurs gave mammals a chance. The Great Dying opened new evolutionary doors. Extinctions are brutal, but they are also creative. They are Earth's way of starting fresh. The story of life isn't a straight line. It's a cycle of growth, destruction, and rebirth. Mass extinctions prove that the planet doesn't cling to the past. It resets and begins again. For over 150 million years, dinosaurs ruled the Earth. They were giants, predators, herbivores, creatures of every shape and size, from towering sauropods to sharp-clawed raptors. They filled the land, the skies, and even the seas. It was their world, but then everything changed. Suddenly, violently. 66 million years ago, a rock from space sealed their fate. A 10-kilometer wide asteroid came screaming through Earth's atmosphere. It slammed into what is now the Yucatan Peninsula in Mexico. The impact crater, called Chicxulub, is still there today, buried beneath rock and ocean. In an instant, the energy released was equal to billions of nuclear bombs. A fireball lit up the skies. Shockwaves flattened forests for thousands of miles. Mega tsunamis tore across coastlines. And the real destruction came after. The asteroid kicked dust, sulfur, and rock vapor high into the atmosphere. A thick blanket covered the Earth. Sunlight dimmed. The planet cooled. Plants withered without light. Food chains collapsed. The dinosaurs, already stressed by volcanic activity and climate shifts, had no chance. The great reptiles that had dominated for so long were gone. Flying pterosaurs vanished too. Marine reptiles disappeared. It was the end of an era, but not all life perished. Some small creatures endured. Mammals, once tiny and hiding in the shadows of dinosaurs, survived. Birds' descendants of small feathered dinosaurs survived too. In fact, every chicken alive today is a living link to those ancient rulers. The extinction of the dinosaurs reshaped everything. It cleared space for new animals to rise. Mammals diversified. They grew larger. They spread across the world. Eventually, primates appeared. And from them, us. Without the asteroid, Earth would look very different. Dinosaurs might still dominate. Humans may never have had a chance. The asteroid was destruction, but also an opportunity, a disaster that made room for new beginnings. And here's the haunting thought: this wasn't the first time Earth was struck, and it won't be the last. Space is full of rocks. Most burn up harmlessly, but every now and then, one is big enough to change history. We owe our existence to a single catastrophic day 66 million years ago. The day an asteroid ended the age of dinosaurs and began the slow rise of humans. A cosmic disaster, a turning point, a reminder that the universe shapes our story in ways we can't control. The dinosaurs may be gone, but their shadow is everywhere, in fossils, in birds, and in the path they cleared for us to exist. The asteroid had ended the age of dinosaurs, but it didn't end life. Some creatures clung to survival, tiny, fur-covered, warm-blooded mammals. For millions of years, they had lived in the shadows. They were small. They hid from predators. They scurried at night, eating insects and plants. They weren't kings of the world. They were survivors, and survival gave them an advantage. When the dust settled, the skies cleared, and dinosaurs were gone. The mammals stepped into the empty world. Suddenly, forests, plains, and oceans were wide open. No T-Rex, no raptors, no giant reptiles to compete with. For the first time in history, mammals had room to grow, and grow they did. Some became fast runners. Some became strong climbers. Some adapted to the water. Mammals began to spread into every environment on Earth. In the ancient forests, small primates appeared early relatives of monkeys and humans. In the seas, mammals like whales and dolphins began their story. On land, rodents, cats, dogs, and hooved animals evolved. Life was experimenting again. What made mammals so successful? Several superpowers. First, warm-blooded bodies. They could survive in cold or hot places. Dinosaurs had once ruled warm climates, but mammals could live everywhere. Second, fur and hair. A built-in blanket. Perfect for survival when Earth's climate shifted. Third, brains. Mammals developed bigger, more complex brains. They could learn, solve problems, and adapt quickly. And finally, caring for their young. Unlike reptiles that lay eggs alone, mammals protect and feed their babies. It gave each new generation a better chance to survive. Over millions of years, these traits turned mammals from tiny survivors into Earth's new rulers. They filled the gaps left behind by dinosaurs, and they kept diversifying. Fast forward through time. Small mammals grew into mammoths. Whales became giants of the ocean. Cats became powerful hunters. Primates started walking upright. One branch of these primates eventually developed tools, fire, language, civilization. That branch was us, humans. Think about it, without the dinosaurs' extinction, none of this would have happened. We owe our existence to both survival and opportunity. A twist of fate, a cosmic accident that gave mammals the stage. The rise of mammals wasn't just a comeback story. It was the beginning of the world we know today. A story that connects ancient survivors to the modern species walking the earth now. From the tiniest mouse to the largest blue whale, all of them trace their victory back to that moment when the dinosaurs fell. The mammals took over, and the world was never the same again. So next time you see your pet dog, or hear the squeak of a mouse, or watch whales breaching in the sea, remember this: they are all survivors of an ancient catastrophe, the heirs of a broken world, and so are we. Don't miss the next chapter of this cosmic story. Hit that subscribe button and keep exploring the universe with us. Earth has never been stable. Its climate swings like a pendulum, hot, cold, oceans rising, then shrinking. Forests grow, then die back. Among the most dramatic changes, the ice ages. Picture this: huge sheets of ice, miles thick, crawling across continents, glaciers grinding down mountains. Rivers are frozen solid. Animals are struggling to survive. And it wasn't just once. Ice ages came and went many times. Each one reshaped Earth. Let's rewind. About 2.4 billion years ago, the first great freeze, called Snowball Earth. Ice stretched all the way to the equator. Our planet looked like a frozen marble hanging in space. Life barely clung on in tiny pockets under the ice. Fast forward, more freezes have happened across Earth's history. The most famous? The Pleistocene Ice Age started about 2.6 million years ago. This wasn't one endless winter. It was cycles. Glaciers advanced, then melted back, again and again. Each cycle lasts tens of thousands of years. During the coldest times, ice covered North America, Europe, and Asia. Sea levels dropped as water locked into ice sheets. Land bridges appeared, letting animals and humans migrate. Then, during warmer swings, the ice retreated, forests spread, oceans rose again. These swings controlled evolution. Animals adapted or vanished. Think about the mighty woolly mammoth. Thick fur, curved tusks, built for the cold. They roamed icy plains, alongside saber-toothed cats and giant ground sloths. But when the ice melted, many couldn't cope. Extinction followed. And humans? Ice ages shaped us too. We learned to hunt in frozen landscapes. We made warm clothing. We built shelters. We controlled the fire. Climate forced us to innovate. And those innovations built the foundation of civilization. But here's the twist. Ice ages aren't random. They follow cycles. The tilt of Earth's axis, the shape of its orbit, the wobble of its spin, even tiny changes in sunlight drive massive swings in climate. Scientists call these Milankovitch cycles. Add in volcanoes, shifting continents, and greenhouse gases, and Earth becomes a climate roller coaster. Today, we're living in a warmer phase between ice ages, but technically, we're still in an ice age. The ice sheets of Antarctica and Greenland are the last reminders. They may seem permanent, but like before, they can grow or vanish depending on what comes next. Ice ages remind us of a truth. Our planet is never still. It breathes in cold. It exhales heat. And life must dance to its rhythm. From frozen Earth to warm jungles, climate has been both destroyer and creator. It has wiped out species and given birth to new ones. Without these swings, mammals might not have risen. Humans might not exist. The frozen epochs were brutal, but they were also necessary, because sometimes, only in the hardest winters, can life find the strength to evolve. Humans are newcomers. In the grand timeline of the universe, we appear almost instantly. Life began billions of years ago. Single cells, then complex organisms, then animals. Dinosaurs ruled. Mammals survived, and finally, primates appeared. About 6 million years ago, our earliest ancestors walked upright in Africa. They were small, clever, and adaptable. They faced predators, climate change, and scarce food. Only the smartest survived. By 2.5 million years ago, early humans, Homo habilis, emerged. They made simple tools. Chipped stones became knives and scrapers. They learned to use fire. Survival demanded innovation. Next came Homo erectus. Larger brains, better tools. They migrated out of Africa. They crossed deserts, mountains, and rivers. They spread across Asia and Europe. By 300 years ago, modern humans, Homo sapiens, had appeared. Brains capable of language, art, and abstract thought. They painted caves. They buried their dead. They began to imagine the world in new ways. Humans adapted to every environment, from icy tundras to dense jungles, from deserts to coastal shores. No other species had spread so fast or so widely. Their rise coincided with challenges. Ice ages forced migrations. Climate shifts demanded creativity. Hunting strategies changed. Tools evolved into spears, bows, and eventually agriculture. Agriculture began about 10,000 years ago. Humans learned to grow food. They built villages, then cities. Civilizations rose along rivers. Sumer, Egypt, China, the Indus Valley. In a blink of cosmic time, humans went from wandering bands to building empires. They invented writing, mathematics, and astronomy. They observed the stars and wondered about their place in the cosmos. Technology accelerated. Stone tools became metal. Metal became machines. The Industrial Revolution reshaped society. Electricity, steam engines, and telegraphs connected the world. In just a few centuries, humans ventured into space. Satellites circled Earth. Humans landed on the moon. Probes reached distant planets. We began to explore the universe that formed billions of years before us. Yet, despite all this, humans remain fragile. Our history is short, but our impact is immense. We alter landscapes. We change climates. We drive species to extinction. Still, humans carry something unique: the ability to imagine, plan, and create, to study the stars, to understand the universe, to look back at the cosmic timeline and see our place. In the blink of cosmic time, humans are here, small and fleeting, but capable of understanding the vastness around them. The universe existed long before us. It will continue long after. But in this brief moment, humans witness it. And in that moment, they write their story. A story of survival. A story of curiosity. A story that connects the tiny spark of life on Earth to the infinite cosmos. Humans have always looked up. The night sky is bright, mysterious, and vast. Stars are countless. The moon glows. The sun rules the day. Long before telescopes, humans watched carefully. Patterns stood out. Some stars formed constellations. Others moved unpredictably. Planets wandered. Ancient people noticed cycles. The moon waxed and waned. The sun rose and set at different points. Seasons changed. These patterns were crucial for survival. Agricultural societies depended on the sky. Knowing when to plant crops was a matter of life or death. They watched the sun, the moon, and the stars. Calendars formed from observations. Stone circles and monuments marked solstices and equinoxes. The Babylonians were pioneers. Around 2000 BCE, they mapped stars. They recorded positions and movements. They predicted eclipses. They believed celestial events influenced life on Earth. In Egypt, the sky guided construction. Pyramids aligned with stars. Temples tracked the sun and stars. Astronomy was intertwined with religion. The heavens were a map of gods and fate. The Greeks took sky watching further. Philosophers asked why planets move. Aristotle and Ptolemy created early models. They imagined Earth at the center. The stars were fixed on a celestial sphere. China also advanced astronomy. They kept detailed records of comets, eclipses, and novae. These records help modern scientists today. Ancient Chinese astronomers were precise and systematic. Star maps became tools for navigation. Seafarers relied on the North Star to guide them. Celestial navigation allowed exploration across oceans. Astronomy was practical as well as philosophical. The night sky inspired myths. Constellations told stories of heroes, monsters, and gods. Stars were more than lights. They were guides, teachers, and symbols. Observation demanded patience. Humans tracked cycles for generations. Slow, careful records led to predictions. Eclipses could be forecast. Planetary positions could be known in advance. By connecting the dots, humans began to see order in the cosmos. They moved from fear of the unknown to understanding patterns. The sky became a canvas of knowledge. Star charts, tablets, and stone monuments preserved this knowledge. These first astronomers laid the foundation. They transformed wonder into study. They asked questions that still guide us today. What are stars? How does the sun move? Are we alone? The dawn of astronomy was not just about stars. It was about curiosity, observation, pattern recognition. It was the first step in humans' understanding of the universe. And it all started with looking up, tracking lights in the sky, drawing maps of the heavens, wondering, imagining, and connecting the dots. The stars became a mirror for humanity's curiosity. From these first sky watchers, modern astronomy would emerge. Telescopes, satellites, and space missions owe their beginnings to those early observers. The night sky inspired science, navigation, and philosophy, and it still inspires us today. Humans always looked up. The sky was full of mystery, but the naked eye could only see so much. Then came the telescope, a simple invention that changed everything. In 1609, Galileo pointed his telescope at the sky. It was crude by today's standards, but it revealed wonders no one had seen. The moon was not smooth. It had mountains, valleys, and craters. Jupiter had moons orbiting it. This challenged the idea that everything revolved around Earth. The universe was bigger than anyone imagined. Galileo also observed the Milky Way. He saw countless stars, impossible to count. The universe suddenly seemed infinite. His discoveries shook the world. Science and observation replaced superstition and assumption. Over time, telescopes improved. Mirrors replaced lenses. Observatories were built on high mountains. This kept telescopes above the clouds and pollution. Astronomers saw farther and clearer than ever before. In the 18th and 19th centuries, telescopes revealed more planets. Uranus was discovered by William Herschel. Saturn's rings became visible in detail. Nebulae, clusters, and galaxies were catalogued. The universe kept expanding before human eyes. Photography changed astronomy in the 19th century. Stars and galaxies could be recorded permanently. Patterns and movements were easier to track. Astronomy became data-driven. The 20th century brought radio and space telescopes. Radio waves revealed invisible parts of the universe. X-rays and infrared opened new windows. Astronomers saw black holes, neutron stars, and distant galaxies. Then came the Hubble Space Telescope in 1990. It floated above Earth's atmosphere, no atmosphere to blur the view. Hubble captured the sharpest images humanity had ever seen. Galaxies millions of light years away became visible. Nebulae glowed in unprecedented detail. The universe's age, structure, and expansion were measured. Hubble confirmed the Big Bang theory. It revealed dark energy accelerating the cosmos. Telescopes changed our perspective. From Galileo's tiny lens to Hubble's orbiting observatory, humans could see farther than ever. We realized we are part of a vast, dynamic universe. Telescopes are still evolving. The James Webb Space Telescope now peers into the first galaxies. Future telescopes will explore exoplanets. They might detect signs of life beyond Earth. All this began with one simple idea: look up. From early sky watchers to Galileo and beyond, curiosity drove discovery. Telescopes transformed wonder into knowledge. They opened a window to the cosmos. The universe is vast. Every new telescope reveals more mysteries, and the journey has only just begun. At the start of the 20th century, physics had questions it couldn't answer. Gravity, light, and motion didn't fully add up. Then came Albert Einstein, a patent clerk with a mind that saw the universe differently. In 1905, Einstein published his special theory of relativity. Time and space were no longer absolute. They were linked. Together, they formed space-time. He proposed something shocking. Time could stretch. Distances could shrink. Speed affects reality. If you move fast enough, time slows for you. Einstein called it time dilation. Light, he said, is constant. It doesn't care how fast you are moving. This challenged centuries of Newtonian thinking. Motion was no longer universal. It became relevant. 10 years later, Einstein expanded his ideas. General relativity explained gravity in a new way. Mass bends space-time. Planets orbit because space-time curves around stars. Gravity is geometry. Black holes, Einstein predicted, were possible. Mass concentrated in a tiny point would warp space-time completely. Nothing could escape its pull, not even light. This was once science fiction. Now, it has become a theoretical reality. Relativity changed our understanding of the cosmos. Time is no longer a ticking clock everywhere. It depends on speed and gravity. The faster you move, or the stronger the gravity, the slower time flows. This isn't just theory. It's measured in GPS satellites today. Einstein also reshaped energy and matter. E-mech squared, the famous equation, showed energy and mass are interchangeable. A tiny bit of matter could release enormous energy. This principle powers the sun and nuclear energy. The universe itself became a dynamic entity. Space could stretch, curve, and warp. Gravity waves, ripples in space-time, were predicted. They were only detected a century later, confirming Einstein's vision. Relativity also explained light bending around stars. In 1919, during a solar eclipse, starlight shifted. Einstein's theory matched observation. The world realized the universe behaves differently than anyone imagined. From black holes to expanding space, from time dilation to gravitational waves, relativity reshaped everything. It changed how we explore the cosmos. It became the foundation of modern astrophysics. Einstein's revolution showed one thing clearly: the universe is stranger than our senses suggest. Time, space, mass, and energy are all connected. We live in a cosmic fabric that stretches and bends. Every discovery since has built on his insight. Telescopes, satellites, and particle accelerators all test relativity. It's not just theory, it's reality. Einstein taught us to question assumptions, to think beyond the obvious, to see the universe as a living, dynamic web of space-time. The cosmos became not just vast, but flexible, alive, and mysterious. Relativity is more than equations. It's a new way to understand everything we observe, and it continues to guide scientists as they explore the universe today. The universe has secrets on every scale. Big things are impressive, but small things are stranger. At the atomic and subatomic level, the rules change. This is the realm of quantum mechanics. Quantum physics began in the early 20th century. Max Planck noticed energy comes in chunks, called quanta. Einstein used the idea to explain light as particles, photons. Suddenly, light could be both a wave and a particle. Niels Bohr studied atoms. Electrons don't orbit like planets. They exist in clouds of probability. We can't know both position and speed exactly. Heisenberg called this the uncertainty principle. Particles behave unpredictably. Sometimes they act like waves, sometimes like particles. This is wave-particle duality. It challenges everything we think about reality. Schrödinger imagined a cat alive and dead at the same time. It illustrated superposition. Particles can exist in multiple states simultaneously until measured. Observation collapses possibilities into reality. Quantum entanglement takes strangeness further. Two particles can be linked across vast distances. Change one, and the other responds instantly. Einstein called it spooky action at a distance. Yet, experiments confirm it happens. Probability, not certainty, rules the quantum world. Electrons don't travel paths. They exist in clouds of probability. Particles pop in and out of existence. Energy fluctuations create temporary particles called virtual particles. Quantum mechanics is not just a theory. It drives modern technology. Semiconductors, lasers, and MRI machines all rely on quantum rules. Computers, smartphones, and LEDs wouldn't exist without it. Quantum tunneling allows particles to pass barriers. Classical physics says it's impossible. Quantum says, watch this. This explains nuclear fusion in the sundae. Quantum mechanics also shaped the Standard Model. It describes fundamental particles, quarks, electrons, and neutrinos. Forces between them are carried by other particles. It's a map of nature's building blocks. Yet many questions remain. Why does quantum behavior dominate small scales but fade at large scales? How does gravity fit with quantum mechanics? These mysteries drive cutting-edge research. Quantum physics teaches us humility. The microscopic world doesn't obey common sense. It's a realm where probabilities rule, not certainties, where observation shapes reality, where connections span space instantly. Understanding quantum mechanics gives insight into the universe's foundation. It's weird, counterintuitive, and mind-bending. Yet it works perfectly, explaining phenomena we couldn't imagine. The quantum world is strange, but it's real. It underpins chemistry, electronics, and even biology. It's the invisible framework of reality. And every discovery brings us closer to understanding the universe at its deepest level. Space isn't empty. It's a flexible fabric called space-time. Massive objects bend it. Einstein predicted this in 1916. His general theory of relativity showed that gravity is geometry. Massive bodies, like stars and black holes, warp space-time. When they accelerate, they create ripples. These are gravitational waves. They travel at light speed across the universe. Disturbances in space-time itself. For decades, gravitational waves were theoretical. They were too tiny to detect. A passing wave stretches and squeezes space by fractions of an atom, almost impossible to measure. Then came LIGO, the Laser Interferometer Gravitational Wave Observatory. Two huge facilities in the United States. Lasers travel kilometers down long arms. Mirrors reflect the light precisely. A passing wave changes the distance by less than a proton's width. Extremely subtle. In September 2015, LIGO detected the first signal. Two black holes collided over 1 billion light-years away. Their merger released energy more powerful than all stars in the observable universe combined for a brief moment. Space-time rippled. Earth felt it. The discovery confirmed Einstein's century-old prediction. It opened a new way to observe the cosmos. Gravitational waves carry information invisible to light. We can now hear events that were once silent. Merging black holes and neutron stars are now within reach. These collisions produce gravitational waves, and sometimes light. Multi-messenger astronomy combines signals from light, gravitational waves, and particles. This gives a complete cosmic story. Gravitational waves travel untouched. Unlike light, they pass through matter freely. No dust or gas blocks them. They reveal hidden events deep in space. Astronomers use waves to study extreme physics. The densest matter, fastest spins, strongest gravity. We can measure black hole masses and spins precisely. We can understand neutron star collisions and the origin of heavy elements like gold and platinum. Future detectors like LISA will listen in space, millions of kilometers apart, free from Earth's noise. They'll detect waves from supermassive black holes and even early universe events. Gravitational waves also test fundamental physics. Do they travel at light speed? Do they obey Einstein's equations exactly? So far, so good. But subtle deviations could reveal new physics. These ripples connect us to the universe in real time. Events billions of years ago reach us now. We are no longer passive observers. We are listeners to the cosmic symphony. Gravitational waves prove the universe is alive. Space itself vibrates with energy and motion. Every collision, every spin, every explosion sends messages across the cosmos. We are learning to decode them. The universe whispers its secrets. Gravitational waves are its voice. Listen carefully, and you can hear the rhythm of creation itself. For centuries, humans wondered if other worlds existed. Planets beyond our solar system were pure speculation. The stars twinkled, silent and distant. Could they host planets like Earth? In the 1990s, technology finally caught up with imagination. Astronomers began to detect planets orbiting distant stars. These are called exoplanets. Thousands have been discovered since. The first confirmed detection was in 1992. 2 planets orbit a pulsar, unusual, extreme worlds. Then, in 1995, 51 Pegasi b became the first exoplanet found around a Sun-like star, a hot Jupiter, a gas giant very close to its star. Unexpectedly, it challenged existing planet formation theories. Exoplanets come in an incredible variety. Gas giants, larger than Jupiter. Small, rocky worlds like Earth and Mars. Some orbit 2 stars, like Tatooine from Star Wars. Others circle their stars so closely that their surfaces are molten. Astronomers use several methods to detect exoplanets. The transit method looks for dips in starlight. A planet passing in front of its star blocks tiny fractions of light. The Kepler Space Telescope used this method to find thousands. The radial velocity method detects tiny wobbles in a star's motion. The gravity of an orbiting planet pulls the star slightly. Direct imaging is harder but possible. Special instruments block starlight to see faint planets nearby. Infrared telescopes detect heat from planets that would otherwise be invisible. Exoplanet studies reveal new insights into planetary systems. Some stars have multiple planets in neat, flat orbits. Others are chaotic, with planets swinging wildly. Some have atmospheres, clouds, even hints of water. The ultimate goal, habitable worlds. Planets in the Goldilocks zone, not too hot, not too cold, where liquid water could exist, where life as we know it might survive. A few promising candidates have been found. Small rocky planets orbiting red dwarfs close to Earth. Future telescopes, like the James Webb Space Telescope, will analyze atmospheres, searching for oxygen, methane, and other biosignatures. A first hint of life beyond Earth may come from these discoveries. Exoplanets challenge our understanding of how common life might be. Are Earth-like worlds rare or plentiful? Each new planet expands the cosmic map. Each discovery is a reminder. The universe is far bigger than our solar system. We now know planets are everywhere. Some strange, some familiar, some unimaginable. Our Sun is just one star among billions, hosting one system. Other stars host their own families of planets. Some may be eerily similar to Earth. Exploration continues. Space telescopes and advanced instruments search for more. The next decades may reveal thousands more worlds. Worlds where oceans ripple, atmospheres shift. Life could exist or once existed. Exoplanets transform our view of the cosmos. They show that Earth is part of a vast, complex universe. We are no longer alone in imagination. The universe is teeming with potential worlds. Life on Earth is fragile. It exists because conditions are just right. Liquid water, stable temperatures, and a protective atmosphere. But is Earth unique? Astronomers look to other worlds. Mars is first on the list. Red, dry, and cold now. But evidence shows it was wetter billions of years ago. Rivers, lakes, and perhaps oceans once existed. Could life have started there? Icy moons are next. Europa, orbiting Jupiter, hides a liquid ocean beneath thick ice. Enceladus, Saturn's moon, shoots water plumes into space. These oceans could host microbial life. Dark, cold, but liquid water is a start. Exoplanets are promising too. Planets in the habitable zone. where water could exist on the surface. Astronomers search for atmospheres. Oxygen, methane, and carbon dioxide could hint at life. Life doesn't need to look like us. Microbes, algae, and extremophiles, they survive in extreme conditions. Acidic lakes, deep oceans, volcanic vents. Life is adaptable. It could thrive in ways we cannot imagine. Space missions focus on biosignatures, chemical traces that suggest life exists or existed. Mars rovers drill, scoop, and analyze soil. Europa Clipper will fly through plumes, checking for organic molecules. James Webb Space Telescope studies exoplanet atmospheres. SETI listens to the stars. Radio signals, laser pulses searching for intelligent life. No confirmed contact yet. But the search expands daily. Extremophiles teach us resilience. Microbes survive in boiling vents, frozen ice, high radiation. If life can adapt on Earth, it might exist elsewhere. Even tiny pockets of life could change everything. The discovery of life would be revolutionary. It would answer the age-old question, are we alone? Even microbes would show that biology is universal. Intelligent life? That remains a bigger mystery. Scientists consider another factor, time. Civilizations may rise and fall before we notice. Signals may be fleeting. Timing is everything. We search for planets with water. We study atmospheres. We monitor distant stars. We send probes to moons and asteroids, all to find life beyond Earth. The universe is vast, billions of stars, each with planets. Even a tiny fraction hosting life means countless living worlds. Life may be common, rare, or hiding in plain sight. The search for life teaches humility. Earth is special. Life is precious. Our existence is a miracle of conditions, chemistry, and time. One day, we may find life elsewhere. Tiny microbes on a distant moon, or intelligent civilizations across the stars. Until then, the search continues. Eyes to the sky, instruments ready, curiosity guiding us. Life beyond Earth may be near or far. Either way, the quest to discover it is one of humanity's greatest adventures. Earth is our home, but space calls. Our planet has limits. Resources, population, climate pressures grow. Humanity looks outward. Colonizing space is no longer science fiction. Moon bases, Mars habitats, orbital stations, plans are real. We already live in microgravity aboard the ISS. We've proven humans can survive beyond Earth. Mars is the first target, a cold desert with thin air. We must terraform, build habitats, or live underground. Water ice exists, and we could extract oxygen. Solar power will feed colonies. Robots will prepare the groundwork. Moon colonies come first, closer, easier to supply. Mining helium-3 for fusion energy is possible. Moon bases can serve as launch points to Mars and beyond, a stepping stone to the stars. Life in space requires adaptation. Gravity affects muscles and bones. Radiation threatens health. Food must be grown or shipped. Air, water, and energy must be recycled. Technology must support survival. Space travel will evolve. Nuclear propulsion, ion engines, and solar sails could shorten journeys. Generation ships may carry hundreds of people on centuries-long trips. Cryosleep might let humans hibernate through long journeys. Beyond the solar system, exoplanets are our goal. Planets in habitable zones with water and moderate climates. Some may require domed cities or underground shelters. Some may allow outdoor living. Exploration and adaptation go hand in hand. Economics matters. Space colonies need resources to survive. Mining asteroids offers metals, water, and fuel. Trade between colonies may become reality. A space economy could flourish. Colonization may protect humanity. A single planet is risky. Asteroids, climate change, or other disasters could end life. Multiple habitats across planets and moons reduce risk. Humanity spreads, survives, and thrives. Ethics are crucial. Do we disrupt alien ecosystems? Who decides colonization rights? How do we ensure fairness across colonies? Exploration comes with responsibility. Education and science drive expansion. Astronomy, biology, engineering, and medicine guide decisions. Robotics and AI reduce risk. Space farming and life support technology sustain life. Culture will evolve. New worlds, new communities, new identities. Language, art, and traditions may diverge. Humanity will become a multi-planet species. The dream of colonizing space inspires generations. It challenges limits and expands imagination. The stars are not unreachable, they are next. Step by step, we move beyond Earth. Humanity's future is among the stars. Survival, exploration, discovery, and adventure await. From the Moon to Mars to distant exoplanets, we will go. Space is vast, but so is human potential. Colonizing space may redefine what it means to be human. Our story continues in the universe. The universe is expanding. Galaxies drift apart. Stars burn fuel and die. Over trillions of years, energy spreads thin. Heat death is not dramatic. No explosions, no flashes, just silence. A slow fade into nothingness. All stars will burn out. Red dwarfs last the longest, trillions of years. Even they will eventually die. Black dwarfs replace them cold, dark remnants. Planets orbit dead stars. No light, no warmth, no life. Solar systems drift aimlessly. Gravity alone guides their slow dance. Matter decays. Protons may eventually vanish. Even atoms break down. The universe becomes empty. Temperature approaches absolute zero. Energy is uniformly spread. No useful work can happen. No engines, no reactions, no life. Galaxies become dark. Stars cease to shine. Black holes remain. They slowly evaporate via Hawking radiation. Black holes die too. Even these giants vanish. The universe grows colder, emptier. Entropy reaches a maximum. Time stretches endlessly. No events mark the passage. No change occurs. Just an eternal frozen void. Space itself expands further. Distances increase beyond comprehension. Galaxies, stars, and planets drift forever apart. Isolation becomes absolute. The universe is still, silent, and empty. All processes stop. Physics reaches a final equilibrium. Nothing new can happen. This is the ultimate fate. Not fiery apocalypse. Not collision or chaos. A quiet, frozen, lonely end. Energy cannot be harnessed. No heat gradients remain. No reactions can occur. The universe is dead in thermodynamic terms. Life cannot survive. Civilizations fade long before. Stars die first. Planets cool. Intelligence vanishes. Yet, this end is unimaginably far away. Trillions of years remain before heat death dominates. Humanity is tiny in this timescale. Our concerns are brief sparks in cosmic history. Heat death teaches perspective. All things change. Nothing lasts forever. Even the universe has a lifespan. Scientists study heat death using physics and mathematics. Thermodynamics predicts the inevitable. Entropy always increases. Disorder rises. Order disappears. Though bleak, heat death is fascinating. It reveals the ultimate consequences of cosmic laws. The universe is patient and inevitable. It marches toward a quiet, final state. Understanding heat death inspires reflection. Humanity's life is precious and fleeting. Stars, planets, and galaxies are temporary. Our existence is a brief wonder in a dying cosmos. The heat death hypothesis reminds us Even the vast universe is not eternal in its current form. Time and energy are finite. Eventually, everything fades into silence. Not all theories predict endless expansion. Some suggest a dramatic finale. The Big Crunch is one such scenario. Gravity fights the expansion. Galaxies pull on each other. If matter is dense enough, it can slow the expansion. Eventually, it could reverse it. The universe begins to shrink. Galaxies move closer. Stars collide. Massive explosions reshape everything. Space itself contracts. Distances shorten. Planets approach the sunday. Black holes draw everything in. Stars burn faster under pressure. Heat rises in collapsing galaxies. Supernovae become frequent. New elements form, briefly lighting the darkness. Matter clumps together. Galaxies merge violently. Clusters collapse. The universe becomes chaotic. Time may behave strangely. From our perspective, events speed up. Processes accelerate as density increases. The universe becomes a pressure cooker. Black holes dominate. They merge into supermassive singularities. Nothing escapes their gravity. Even light cannot survive. Everything approaches a single point. The universe's contents are compressed. Density and temperature rise infinitely. Physics, as we know it, breaks down. Eventually, the universe collapses fully. Space itself vanishes. Matter, energy, time all converge. A singularity forms, similar to the Big Bang's start. Some theorists speculate on a cycle. The Big Crunch could trigger another Big Bang. The universe might bounce back. Expansion begins again in a new era. Life cannot survive this process. Stars die, planets collide, civilizations are erased. The collapse is total and unstoppable. All memory of past structures is lost. The Big Crunch is the opposite to heat death. One is quiet and cold. The other is violent and dense. Both are possible fates based on cosmic parameters. Dark energy complicates this theory. If dark energy dominates, expansion may never reverse. But if matter is dense enough, gravity wins. Then the Big Crunch becomes inevitable. This scenario reminds us of cosmic fragility. Even the universe is not permanent in its current form. Everything has a beginning and an end. Cycles of creation and destruction may be natural. Studying the Big Crunch challenges physics. It tests general relativity and quantum mechanics. It pushes understanding of singularities and extreme conditions. It is a playground for theoretical cosmologists. Ultimately, the Big Crunch is a story of reversal. From expansion to collapse, from light and space to darkness and singularity. A mirror of the universe's birth. It shows that endings can be dramatic. Not all cosmic deaths are quiet. Some may implode spectacularly. The universe itself may rewind. Not all endings are slow. Some are violent. The Big Rip is one such fate. Dark energy drives the universe's expansion. It pushes galaxies apart. If dark energy grows stronger over time, things get extreme. The expansion could accelerate without limit. Galaxies drift away faster and faster. Stars inside galaxies feel the pull of expansion. Eventually, galaxies themselves cannot hold together. They stretch apart. Next, stars drift from each other. Solar systems unravel. Planets leave orbits. Gravity loses its grip entirely. The sun can no longer hold planets. Earth could drift alone in space. Moons escape their planets. Everything becomes isolated. Even atoms feel the strain. Electrons separate from nuclei. Molecules break apart. Matter itself comes undone. Time and space stretch violently. Distances become infinite. The universe is ripped at its core. Nothing remains in one place. The process starts large and scales down. Clusters of galaxies break first, then stars, then planets, then molecules. Finally, the fabric of space-time itself tears. The Big Rip is faster than the heat death. It is the opposite of collapse. Instead of slow cooling, it is sudden destruction. All structure is annihilated. Calculations depend on dark energy's nature. If it increases over time, the Big Rip is inevitable. If it stays constant, expansion continues but not violently. Observations are ongoing to find out which path we are on. This fate is terrifying. Life, planets, stars, everything disappears. Not just structures, but space itself. A universe without form, without matter, without time. The Big Rip also tests physics. It challenges general relativity and quantum mechanics. Extremes of energy and expansion push theories to the limit. Cosmologists try to predict when it could happen. Some estimates suggest billions of years from now. Galaxies first, then solar systems, finally atoms. The universe is literally torn apart from the largest scales to the smallest. It is a story of ultimate force, a reminder that the cosmos is not static. It is dynamic, evolving, and sometimes violent. Even the space between stars is not safe. The Big Rip shows the universe's fragility. Not every ending is quiet or slow. Some endings are explosive, destructive, and final. Expansion itself becomes the destroyer. No life, no planets, no stars, just endless stretching. Time continues, but matter cannot exist. Space-time itself becomes a ghost. The universe, once full of structure, ends in chaos. The Big Rip is a stark warning. Cosmic forces are immense. Even space-time is not eternal. One day, the universe could tear itself apart. Our minds are restless, always reaching, always searching. We see a cloud and turn it into a shape, a rabbit, a ship, a dragon drifting in the sky. We look at the stars, random points of light, and we connect them into constellations, stories drawn across the night. Imagination is our tool for making sense. It turns chaos into a pattern. It makes the unfamiliar feel known, but sometimes we forget. The patterns are ours. We placed them there. We made them real in our minds. That doesn't make them less powerful. In fact, it may make them more powerful, because imagination is design, not in stone or metal, but in meaning. When a child picks up a stick, it becomes a sword, or a wand, or a tool from a future that hasn't happened yet. That's design, not discovered, not inherited, created. Our ancestors looked at fire. They didn't just see flames. They imagined warmth, safety, cooking, and light. They imagined the possibility, and then they designed their lives around it. The wheel, the bow, the sail, these began as thoughts, as what if, as imagination takes shape. Even science begins this way. A question no one asked before, a possibility no one has tested yet. The imagination sparks the experiment, and the result reshapes the world. Imagination is how humans create their own version of order. It's how we design not just tools, but societies, languages, music, and stories. Think about myths. Every culture invented its own explanations. Gods of thunder, rivers that sing, spirits in the wind. These weren't random. They were designs of the mind. The human mind cannot stop drawing blueprints. Even when nothing else is there, we map, we structure, we explain, we dream. But here's the quiet truth. Imagination does not require reality. It creates its own. We see intention where there may be none. We see faces in tree bark, voices in the hum of machines, meaning in the randomness of dice. This is not a weakness. It is creativity. It is the spark that separates survival from wonder. Imagination is what lets us ask, was Earth designed? Because maybe Earth doesn't answer. Maybe Earth just exists. But we ask anyway. We imagine purpose. We imagine a story, and that itself becomes design. If the universe is random, we design it into meaning. If the universe is structured, we translate that structure into art. Either way, our role is the same. We imagine, we design, we make the invisible visible. When you look at Earth tonight, when you listen to this voice, you are part of that design because you are imagining along with me. You are filling silence with a story. You are shaping reality in your mind. That's the gift we carry, the blueprint of imagination, a design not imposed, but invented. And maybe that's enough. Maybe the power of imagination is the answer itself. Not whether Earth was designed, but we design it every day with our thoughts. So, hold that idea gently. Your mind is not just observing the universe, it's shaping it. It's adding a pattern, meaning, story. That is the human touch of design. And if you'd like to keep traveling through questions like this, don't forget to subscribe. Because imagination doesn't end here. It continues. With every story, every question, every dream. Sleep well, and let your imagination design the rest. Look around. At first, the world feels messy, chaotic, unpredictable, but then patterns appear. The petals of a flower, the spiral of a shell, the curve of a wave, the rhythm of a heartbeat. Hidden inside it, all is a language. Not spoken, not sung, written in numbers. Mathematics. Math feels different from words. Words change, languages evolve. But math, it stays. 2 plus 2 is always 4. A circle is always 360 degrees. A prime number is prime, no matter the tongue. That's why people call it the blueprint of reality. Because it doesn't just describe the world, it predicts it. Drop a ball, and gravity follows an equation. Planets orbit, and the math fits perfectly. Even light bends along mathematical lines. Einstein once said, "The most incomprehensible thing about the universe is that it is comprehensible." And he meant this: the universe speaks math, and somehow we understand it. But here's the mystery. Did we invent math, or did we discover it? Is math a tool we built, like a hammer or a compass? Or is it the fabric of reality itself, waiting for us to notice? Think about 0, a nothing that means something. Think about infinity, a number that never ends. We can imagine them, we can calculate with them, but do they truly exist in the universe, or only in our minds? Now consider pi, the ratio of a circle's circumference to its diameter, 3.14159, and on forever. No matter where you measure, no matter what circle you draw, pi is there, hidden, unchanging. It feels less like an invention and more like a discovery, as if circles were whispering a secret we finally heard. The same with the Fibonacci sequence. 1, 1, 2, 3, 5, 8, 13. It appears in sunflowers, pine cones, hurricanes, and galaxies. Math in nature, design in growth. Mathematics builds bridges and rockets, but it also builds understanding. It explains why snowflakes form symmetries, why rainbows bend light, why black holes curve space-time. Even chaos has math, fractals, equations that describe infinite complexity, clouds, mountains, rivers, all shaped by the hidden hand of numbers. Sometimes math feels cold, abstract, symbols on paper, but it is also art. It has elegance, beauty. A simple formula can explain something vast. E mech squared. So small, so powerful, it makes you wonder, if aliens exist and we meet them, what language will we share? Not English, not Mandarin, not sound at all, but mathematics, because math is universal. A circle is a circle anywhere in the cosmos. A prime is a prime, whether on Earth or a distant galaxy. But here's another thought. Maybe math is not the blueprint. Maybe it's the lens. A way for humans to understand, to turn the unknown into something knowable. The blueprint might be deeper still, beyond numbers, beyond symbols, yet math keeps guiding us forward, Every leap in science comes through it. Every spacecraft, every theory, every model of the universe. Mathematics is more than calculation. It is a connection between the mind and the cosmos, between thought and reality. So the next time you see a spiral shell, or a starry night, or even the ticking of a clock, remember, you are watching mathematics at work. You are watching the blueprint unfold. And that blueprint is endless, waiting for us to keep reading it, digit by digit, equation by equation. If the universe is a book, then mathematics is its language. And we are just beginning to learn how to read it. Listen closely, not with your ears, with your imagination, because the universe is playing. Everywhere there is vibration. Everywhere there is rhythm, and together they create music. On Earth, music begins with sound. Strings plucked, drums struck, air vibrating through flutes. But cosmic music is different. It's deeper. It's everywhere. Atoms hum with energy. Electrons jump levels like notes on a scale. Their frequencies are absolute, tiny, invisible songs. Planets, too, have rhythms. Earth rotates once a day. It orbits once a year. The moon pulls the tides like a bass drum keeping time. Stars pulse. Some expand and contract, beating like cosmic hearts. Astronomers call them variable stars. We call them cosmic metronomes. Black holes, strange as they are, also sing. When matter spirals into them, it vibrates space-time. The ripples we call gravitational waves are the universe's bass notes. Low, deep, powerful. NASA has even turned cosmic data into sound. Radio waves from planets, X-rays from stars, the hum of the Milky Way itself. Convert them to frequencies we can hear, and the cosmos becomes a symphony. This isn't poetry alone, it's physics. Every vibration has a frequency. Every frequency can resonate. Resonance creates harmony. Think of a wine glass shattering when a singer hits the right note. The voice resonates with the glass. Now scale that up. Planets and moons resonate in orbits. Jupiter's moons lock into rhythms. For every orbit of Ganymede, Europa orbits twice, Io orbits 4 times. Cosmic harmony written in motion. Even galaxies dance. Clusters spin. Arms spiral. Gravity pulls them into patterns. It is not random. It is rhythm. It is resonance. Pythagoras, thousands of years ago, it spoke of the music of the spheres. He imagined planets and stars producing tones. As they moved through the heavens, he had no telescope, no equations, but he sensed something true, that the cosmos was not silent, that it vibrated with harmony. And modern science agrees. From quantum strings vibrating to gravitational waves echoing, the universe is vibration, resonance, music. Even silence has a tone. Cosmic microwave background radiation. The faint afterglow of the Big Bang. It hums at a frequency. The first note of creation, still echoing today. This idea changes how we see ourselves. Because music is not just out there, we are part of it. Our atoms vibrate. Our hearts beat in rhythm. Our brainwaves oscillate like melodies. We don't just hear the universe's music. We play in it. Think about it. A violin string vibrates, producing harmony. So does a spiral galaxy. So does a wave of probability in quantum mechanics. Different scales, same principle. The universe doesn't need an orchestra. It is the orchestra. Every object is an instrument. Every vibration is a note. Every orbit is a rhythm. Every collapse is a drumbeat. Every birth of a star, a rising crescendo. And what's most striking is this. The music is ongoing. It doesn't stop. It doesn't need an audience. But here we are, aware, listening, translating. So, the next time you hear music, a song, a symphony, a single note drifting in the air, remember, it's not separate from the cosmos. It's part of it, a reflection of the same principles that guide galaxies, stars, and atoms. The universe is not silent. It never was. It hums. It pulses. It resonates. It sings. And whether you call it science, or poetry, or the voice of creation itself, we are lucky to hear even a small part of the song. The music of the universe is endless, and we are inside it. Close your eyes. Notice the thoughts appearing. Memories, images, feelings, awareness. Itself. Where does it come from? That's the puzzle. Science explains the brain as neurons firing, chemical signals, electrical impulses. But the experience of being aware, that's harder. That's the hard problem of consciousness. Why should matter think? Why should atoms care? Why should the firing of neurons feel like anything at all? Some argue it's an illusion. That awareness is just the byproduct of biology, like steam rising from boiling water. Not essential, just extra. But others wonder, could consciousness itself be evidence, not of illusion, but of deeper order? Think about it. The universe is made of particles, of matter, of energy, and yet, somehow, it produces minds. Minds that can imagine, minds that can dream, minds that can ask, why? Awareness might be the strangest outcome of all. Because stars don't reflect, rocks don't plan, atoms don't wonder about meaning. But you do. Maybe this awareness is a hint, a clue. The universe has layers we don't yet understand. Some theories suggest consciousness is emergent. It arises when systems are complex enough, like a flame appears when wood burns. Neurons organize, and suddenly awareness happens. But others suggest it's fundamental, that consciousness is not an accident, but a building block, as real as space, time, and energy. Some call this panpsychism, that every bit of reality has a spark of experience, small, faint, but present. If that's true, then awareness isn't just in your head. It's woven into the fabric of reality. You are not separate from the cosmos. You are its eyes. It's a mirror. It's a witness. This is where philosophy meets science. Because neuroscience measures signals, physics measures energy, but consciousness, it resists simple measurement. Yet here at Ireland, every day, every second, the undeniable fact that you are aware. Some scientists argue this awareness is evidence of design. Not proof, but evidence. Because what are the odds that a blind, indifferent cosmos would produce something that can question itself? Others push back. They say, of course, we're aware. If we weren't, we wouldn't be here to ask. This is the anthropic principle. It explains the puzzle without a deeper mystery. Or does it? Awareness is not just survival. It's poetry. It's a wonder. It's creativity. It's laughter. It's love. Why should random processes create something so rich? Consciousness allows the universe to know itself. Carl Sagan said it best. We are a way for the cosmos to know itself. That might be a metaphor, or it might be literal. Imagine the universe unfolding for billions of years. Stars forming, planets spinning, life crawling, and eventually, awareness waking up, like the universe opening its eyes. Maybe that's the point, or maybe it's just a chance. But either way, it feels extraordinary. When you reflect, you are doing something the stars cannot. When you wonder, you are doing something galaxies cannot. When you ask if Earth was designed, you are participating in the mystery itself. Consciousness may not prove design, but it changes the question, because even if the universe is indifferent, awareness makes it meaningful. You are proof of that. Your awareness is the evidence, whether of design or of emergence, or of something stranger still. And maybe the deeper truth is this: the universe doesn't just exist, it notices through you. We like order, we crave patterns, we want the universe to be neat, predictable, and safe. But the truth? Chaos is everywhere, and without it, life as we know it might not exist. Think about evolution. It's not a straight line. It's trial and error, mutation, failure, survival. Random changes in DNA create new traits. Most go nowhere. Some unlock survival. That randomness, chaos, is the engine of diversity. Even the cosmos itself began with chaos. The Big Bang wasn't tidy. Matter flung everywhere. Galaxies clumped unevenly. Stars formed where the chance density was higher. If it had been perfectly smooth, no stars, no planets, no us. Chaos drives creativity. Artists know it. Writers know it. Musicians know it. A mistake, an accident, a disruption often becomes the spark for something new. Nature works the same way. Forests burn, volcanoes erupt, rivers flood. At first destruction, but then renewal. Ash makes soil fertile. Floods carve new paths. Life adapts. Chaos forces resilience. Chaos theory even gave us a famous symbol, the butterfly effect. A butterfly flaps its wings, and weeks later, a storm forms across the globe. Tiny shifts ripple into massive outcomes. Disorder is not meaningless. It's sensitive. It creates surprising patterns. Look closer at chaos, and you'll often find hidden order. Fractals are a perfect example. Messy, irregular, infinite detail. But zoom out, and you see repeating geometry. Mountains, coastlines, clouds, all shaped by chaotic rules that still produce beauty. Human life is touched by chaos too. Think of history, wars, revolutions, collapses. Messy, painful, unpredictable. But from that turmoil come new ideas, new systems, new freedoms. Chaos disrupts the old to make space for the new. Even your own story follows this rhythm. The times you thought you'd lost everything, maybe those were the moments that set the stage for growth. A broken path, a sudden change, a collapse that forced reinvention. Chaos hurt, but it also built you. Here's the paradox. Too many orders is deadly. A perfectly rigid system breaks under pressure. A perfectly still pond suffocates. But too much chaos? That's also ruined. The magic is in the balance. Enough order to hold structure. Enough chaos to drive adaptation. The universe itself seems to know this. Stars burn steadily, but not forever. Galaxies swirl in unpredictable spirals. Planets wobble just enough to stir climates. Life thrives on the edge between chaos and order. So when we ask, was Earth designed? Chaos is part of the answer. Because a perfect design, free of flaws or randomness, might never have allowed life to evolve. It's the cracks, the turbulence, the instability that made creativity possible. Chaos is not the opposite of meaning. It's the raw material. It's the canvas splattered with paint that slowly reveals an image. The storm clears. The forest regrows. The broken heart heals. And in the aftermath, something new has been born. Disorder is not just destruction, it is creation in disguise. The universe builds by breaking. It grows by shattering. It is designed by experimenting. So maybe chaos isn't the enemy of design. Maybe it is the very tool by which design unfolds. Without chaos, there would be no stars, no forests, no music, no you. Chaos is not failure. Chaos is the spark. If Earth were designed, then nature itself is the classroom. Every leaf, every river, every storm is a lesson waiting to be read. Ecosystems whisper wisdom. Forests show balance. Every tree connects underground, sharing nutrients through fungal networks. Competition exists, yes, but cooperation runs deeper. The forest thrives, not because one tree wins, but because all survive together. The ocean has its lessons too. Currents move like veins, distributing heat energy, and life. Coral reefs, though fragile, build vast cities of stone. Fish find homes. Predators patrol. Even the smallest plankton carries the food chain. The sea teaches scale. Tiny things can hold worlds together. Cycles are teachers of patience. The water cycle spins endlessly. Evaporation, condensation, rain. Always moving, always renewing. Seasons turn with rhythm. Spring births. Summer grows. Autumn releases. Winter rests. Nothing wasted, nothing static. Disasters also instruct. A wildfire destroys. But after, the soil is richer. Seeds, long dormant, burst awake. Life returns stronger. Nature shows that endings are often beginning wearing masks. Resilience is everywhere. Look at moss on stone. Look at the weeds in sidewalk cracks. Life doesn't need perfect conditions. It finds a way again and again. That persistence is nature's deepest lesson. Survival is creativity. Even predators teach. Wolves, once feared as destroyers, actually heal ecosystems. Their hunting keeps prey in check. Deer stop overgrazing. Plants regrow. Rivers stabilize. The wolf teaches balance through pressure. Nature also models efficiency. A spider's web is stronger than steel by weight. A honeybee builds hexagons, the most efficient shape in geometry. Termites design mounds with perfect ventilation. These are not random accidents. They are experiments refined by time, design born from trial, passed on through resilience. But perhaps the greatest lesson is humility. Mountains remind us of scale. Storms remind us of fragility. Nature existed long before humans, and it will remain long after. We are students, not masters. When we mimic nature, we thrive. Biomimicry has given us planes shaped like birds, solar panels modelled on leaves, and self-healing materials inspired by skin. Nature teaches not with words, but with blueprints we can study. Cycles in nature also mirror cycles in us. We grow, we age, we rest, we begin again, just like the tides, just like the moon. Our own biology remembers the rhythms of Earth. If Earth were designed, the design is not written in books. It's etched into rivers, woven into roots, painted across the sky. Nature is the teacher we often ignore. To listen, we must slow down. To learn, we must observe. The ant carries 10 times its weight. The tree bends, but not breaking in storms. The bird migrating across continents is guided by stars. Each is a lesson in perseverance, adaptation, and trust in the greater cycle. Maybe the question isn't whether Earth was designed. Maybe the better question is, are we paying attention to its teachings? Because the answers may already be here, in the forest, in the ocean, in the soil beneath our feet. The design, if there is one, isn't hidden. It's alive, breathing, always showing us how to live. Nature doesn't just sustain us, it instructs us. And the lesson is simple: adapt, balance, renew. That is the wisdom of Earth. That is the teacher we must not forget. Time. We live inside it. We measure it, track it, worry about it. But do we understand it? Why does time move forward? Why not backward? The laws of physics mostly work both ways. Equations don't care about direction, yet our lives do. We remember the past, not the future. We age, we move forward. This is the arrow of time. It's tied to entropy. Order collapses into disorder. A glass falls, and it shatters. Shards don't leap back into shape. The universe drifts from neat beginnings into chaos. That one-way slide gives time direction. But is entropy the whole story? Einstein showed that time bends. Gravity slows it down. Clocks tick differently on mountaintops than at sea level. Travel near light speed, and time itself stretches. What we call now isn't universal. It's personal. Time is relative. Quantum mechanics adds more puzzles. Particles don't seem to care about time's flow. Some equations let effects precede causes. At the most minor scales, the arrow blurs. Time looks less like a straight road, more like a web. Then there's the beginning. Did time start at the Big Bang? Before expansion, was there a before? Or did time itself ignite with space? If so, asking what came before might not even make sense. And the end? If the universe dies, does time die with it? In heat death, no change remains. If nothing happens, is there still time? Or does time require events? To be real, the flow of time feels obvious. We experience it every second. But physicists wonder if flow is an illusion. What if all moments, past, present, future, exist at once? A block universe. We walk through it like frames of film. We feel motion, but the film is already there. That would mean the future is as real as the past. Choice, free will, destiny. Suddenly tangled. Do we decide, or just move through what's already written? Other thinkers flip it. What if time emerges from change itself? If nothing changed, there'd be no time. Maybe time is a side effect, not a foundation. Mystics and philosophers take it further. For them, time is flexible. Moments of awe feel eternal. Moments of suffering feel endless. Our minds stretch and shrink time. Experience bends it as much as physics does. So, is time designed? Its arrow, its relativity, its ties to entropy. These rules structure reality. They allow stars to form, planets to orbit, life to grow. Without time's direction, there's no evolution, no history, no story. The mystery is that we live inside it, yet we can't step outside to look at it. A fish knows water, but cannot escape it. We know time, but never beyond it. And still, we measure it, slice it into hours, tie our lives to clocks. We build machines to test their limits. We dream of traveling through it. But maybe time isn't a road to walk. Maybe it's the fabric itself, the stage where the play unfolds. If Earth were designed, then time is the script. It doesn't just mark moments. It shapes reality. It gives order, direction, meaning. The great mystery remains. Why does time flow? Why does it exist at all? We don't know, but maybe we don't need to. Maybe it's enough to feel the seconds pass, to live inside the rhythm, and to marvel at the gift of the now. What if Earth weren't like this? What if the universe followed different rules? Physics gives us boundaries, but imagination lets us wander beyond them. Picture a world without gravity. Objects float forever. Planets never form. Stars never ignite. Life, it would struggle to anchor itself anywhere. Yet, maybe it would drift, cloud-like, gathering energy in strange ways. Now, imagine stronger gravity, 10 times what we know. Walking would crush us. Mountains couldn't rise. Stars would burn hotter, faster. Civilizations might live short, intense lives, under skies that change rapidly. Change the speed of light. If it were slower, causality would stretch, signals crawl. The universe feels sluggish. If faster, galaxies would evolve differently. Distances would shrink in terms of communication. Perhaps interstellar travel would be trivial. Think of a world with 2 suns. One sun's waiting speed, perpetual daylight, shadows bending, overlapping. No night sky for early astronomers. No dark canvas to wonder at. Would humans, or their equivalents, ever think about stars beyond? Or picture a planet tidally locked. One side burns endlessly in sunlight, the other freezes in eternal darkness. Life might cling to the twilight zone, a thin ring of balance. Civilizations trapped in a narrow band, between extremes. What if chemistry played differently? Not carbon-based life, But silicon, bones like stone, blood flowing like liquid crystal, being slow, durable, thinking in timescales longer than human history. Or what if water wasn't the solvent of life? What if ammonia or methane did the job? Cold worlds, icy seas, alien biology we could barely imagine. Life, but with rules foreign to ours. Flip the constants. If electromagnetism were weaker, atoms wouldn't bind the same. Matter itself might not exist in stable form. If stronger, chemistry could be wildly different. Complexity might never arise. The sweet spot we live in is only one version. Consider universes with more than 3 dimensions, 4, 5, or 10 directions to move. Our minds can't truly picture it, but physics suggests higher dimensions exist. Maybe in those universes, creatures stretch in ways we can't comprehend. Their reality would look like chaos to us. Now, shrink it down. Imagine a world where time doesn't flow linearly. What if moments loop? What if the cause and effect circle endlessly? Civilizations might never understand beginnings or endings. Stories could have no arcs. History could replay itself infinitely. Alternate designs are not just daydreams. They reveal how tuned our own world island. Every small change in physics could erase stars, planets, or life. Yet, in theory, other rules could still create something different, strange, but possible. We ask, were the laws chosen, or did countless universes sprout, each with their own set? If so, we happen to live in one that supports life, not because it's special, but because only here can beings like us exist to ask. Alternate designs also remind us of humility. We see Earth as the default, but really, it's one outcome among many, a narrow balance in an ocean of possibility. Imagining these worlds is more than science fiction. It's a way of probing our own, to ask why gravity is this strong, why does light move this fast, why water flows the way it does. Maybe the design isn't fixed. Maybe it's part of a spectrum, a multiverse of experiments. Each one rolls the dice, with different rules. Some collapse instantly, some simmer with potential, and one ours gives rise to oceans, forests, and human thought. The truth, we don't know if these alternates exist, but thinking about them teaches us how precarious, how astonishing our own design really. Island, if Earth feels designed, then it feels entrusted, not just given, but given the responsibility. Look around. Mountains, oceans, forests, rivers, a system that sustains life, the air we can breathe, water that cycles endlessly, soil that grows food. It feels too precise to waste. And yet, we cut forests, we pollute rivers, we heat the atmosphere. We act like the design is disposable, but it's not. It's fragile. If Earth carries even a hint of design, then protecting it is not optional. It's a duty. Stewardship, not ownership. Think of a masterpiece painting. You wouldn't spray graffiti on it. Think of an ancient temple. You wouldn't knock it down for fun. Earth is both art and sanctuary. Our survival depends on it. Responsibility starts small. Every choice counts. How we use energy, how we treat waste, what we consume, and what we conserve. But it also scales. Nations must act. Industries must adapt. Technology must innovate. Because damage doesn't stay local. Pollution crosses borders. Warming shifts the weather everywhere. Oceans rise for all. We often ask, what if Earth is the only one? What if no other planet sustains us? No backup, no reset button. Then every tree matters. Every coral reef matters. Every breath of clean air matters. Responsibility is more than fear. It's gratitude. Gratitude for rain, for sunrise, for seasons, for a sky filled with oxygen instead of poison. These are not guarantees. They are gifts. Some say humans are too small to matter. But look at our impact. We've shifted climates. We've changed rivers. We've carved mountains. If we can destroy, we can also heal. Responsibility means balance. Not abandoning technology, but using it wisely. Not rejecting progress, but steering it towards sustainability. Electric cars, renewable power, circular economies, all signs that we can evolve. We are not separate from the design. We are inside it. Every breath, every bite of food, every drop of water reminds us Earth doesn't need us, but we need Earth. Children will inherit what we leave. A garden or a wasteland, a home or a warning. Responsibility is not just for now, but for them. Even if Earth weren't designed, responsibility still stands, because it's the only home we have. Whether cosmic accident or divine creation, it deserves respect. It deserves protection. Responsibility is also wonderful. Pausing to see the stars, listening to waves crash, watching a forest sway in the wind. These moments remind us, why do we protect in the first place? Maybe Earth is a test, not of science, but of wisdom. Do we honor what sustains us, or do we take until it's gone? If Earth feels designed, then it feels sacred. Sacred doesn't mean untouchable. It means cared for, protected, cherished. Our duty is simple: to live in a way that doesn't erase tomorrow, to ensure the design, whether cosmic or accidental, continues to thrive. Because when Earth thrives, so do we. In the end, we circle back to the beginning, the question that started it all. Was Earth designed? We've explored patterns in nature. We've traced physics, chaos, and order. We've looked at consciousness, at the time, at galaxies, at atoms. We've seen perfection, and we've seen flaws. The evidence is powerful, but not final. Some things whisper design, symmetry, balance, fine-tuning. Other things shout randomness, mutation, imperfection, chance. The truth? It's not settled, and maybe that's the point. Humans want certainty. We crave answers, like a map through the unknown. But the universe doesn't hand out maps. It gives us mysteries instead, questions layered on questions. Every answer opens a new door. Design or not, the wonder lies in asking, in staying curious, in refusing to let the question die. Think of the night sky. You don't need to know every star's name to feel awe. You don't need to solve the cosmos to be moved by its beauty. The question itself is enough to shift your perspective. Was Earth designed? The scientist asks with equations. The philosopher asks with logic. The poet asks with metaphors. The believer asks with faith. The skeptic asks with doubt. Each version is valid. Each adds to the conversation. But no one has the final word. Maybe one day we'll know. Maybe evidence will tip the scales. Or maybe the question will remain forever open, woven into the fabric of being human. And that's humbling, because uncertainty teaches us something rare: acceptance. We don't need to control every answer. We don't need to box the universe into a neat explanation. We can live with mystery. Wonder doesn't shrink when unanswered. It grows. It expands, just like the cosmos itself. To ask, was Earth designed, is really to ask, what does it mean to be alive? Right here, right now, to breathe air, to walk on soil, to look up and know you are part of something vast. Whether by intention or accident, life is a marvel. The question of design reminds us to notice, to pause, to reflect, to protect, to dream. Maybe design isn't a yes or no. Maybe it's a spectrum. Maybe reality is both structured and chaotic, both purposeful and accidental. A blend that defies simple labels. And maybe that's more beautiful than a clear answer could ever be. So tonight, let the question rest. Not solved, but alive. Not answered, but glowing with possibility. Because the open question is what keeps us looking up. It's what keeps science moving. It's what keeps philosophy burning. It's what keeps wonder alive. Earth may be designed, or not, but asking, that's the real design of being human. Take a moment and look up. The stars above are older than time itself. They were born billions of years ago. Some are gone now, their light still traveling to us. Every atom in your body has a cosmic story. Hydrogen, oxygen, carbon, they were forged in stars. Supernova explosions scattered them across space. Your very being is made from stardust. The universe is vast. Galaxies stretch across unimaginable distances. Time moves differently in its depths. Yet here we are, conscious and curious. We've explored the skies, mapped planets, and studied light from distant galaxies. We've unlocked the secrets of black holes, dark matter, and cosmic expansion. And still, every discovery raises new questions. The cosmos is infinite, and our knowledge is just a tiny spark. Life on Earth is fragile. A single asteroid, a massive eruption, a climate shift, these could change everything. Yet life persists. We adapt, we evolve, we survive. Humans are a fleeting moment in cosmic time, but in this moment, we observe, we imagine, we dream. We reach out to the stars, not just for survival, but to understand who we are and where we come from. We are connected to everything. The elements in our bodies, the air we breathe, the oceans that cover the earth, all are products of cosmic events. Every heartbeat echoes the universe's ancient rhythms. Our future is tied to the cosmos. Maybe one day we will colonize other worlds. Perhaps our descendants will explore galaxies far beyond the Milky Way. Even as stars die and galaxies collide, intelligent life may endure. And yet, we must remember humility. We are small. Our planet is fragile. The universe does not revolve around us. We are observers, travelers, stardust aware of itself. This is our story, born from explosions of light and matter, carrying the essence of stars, living briefly in a vast, ever-changing cosmos, trying to understand the infinite. So look up tonight. Remember that every star is a part of your history. Every planet, every moon, every black hole is a chapter in the same story. We are not separate from the universe, we are its children. And as you reflect on this, know that the journey is far from over. Curiosity will drive humanity further, discovery will light our path, and the stars will always be our guide. If you've enjoyed this journey through space and time, don't forget to subscribe for more cosmic adventures. There's always more to learn, more to wonder about, and more of the universe to explore. We are stardust, we are observers, and we are alive in the infinite.